There is a strange irony at the heart of archaeology. The more evidence we uncover, the more mysteries we seem to create. A newly discovered city raises questions about who built it. A hidden chamber forces historians to rethink a monument they believed they understood. A forgotten inscription introduces names, events, and ideas that appear nowhere else in the historical record. Rather than closing the book on the ancient world, each discovery often opens another chapter, and after centuries of excavation, researchers are increasingly realizing that history is not a complete archive. It is a collection of surviving fragments. Between those fragments are gaps large enough to hide lost technologies, forgotten cultures, and stories that may never be fully recovered. Northwestern Spain. Hidden among the mountains of Leon stands a landscape that looks like the aftermath of a gigantic explosion. Towering red cliffs, shattered peaks, and collapsed valleys stretch across more than 3,000 hectares. But these formations were not created by nature. Nearly 2,000 years ago, the Roman Empire deliberately destroyed entire mountains here in search of gold. The site is known as Las Medullas, and it remains one of the largest engineering projects of the ancient world. Yet despite decades of archaeological research, many experts still struggle to explain how Roman engineers achieved such precision using technologies that should have been far too primitive for a project of this scale. The dramatic ruins had been visible for centuries, but systematic archaeological investigations during the 19th and 20th centuries revealed that the landscape itself was artificial. Researchers discovered hundreds of tunnels, reservoirs, canals, and mining structures hidden beneath the mountains. What initially appeared to be a natural geological formation turned out to be the remains of an enormous industrial operation that transformed an entire region of Spain. Ancient Roman writer Pliny the Elder described a mining technique known as ruina montium meaning the wrecking of mountains. According to his account, Roman engineers excavated extensive tunnel networks deep inside mountain slopes, and water was then released into these underground chambers at high speed. The sudden pressure compressed trapped air and destabilized the rock mass from within, causing entire mountains to collapse under their own weight. Modern geotechnical engineers often compare the process to a controlled explosion, except no explosives were involved. The astonishing part is that this technique required a practical understanding of rock mechanics, internal pressure, fracture propagation, and structural instability, concepts formerly studied in engineering today. Yet Roman miners developed an effective version of the method nearly 2 millennia before modern geology existed. How they determined where to excavate, how much water to use, and how to predict collapse behavior remains only partially understood. The destruction of mountains required enormous quantities of water. To obtain it, Roman engineers built one of the most ambitious hydraulic systems in the ancient world. Archaeologists have identified canal systems extending well over 100 kilometers, with some estimates exceeding 300 kilometers when secondary channels are included. These canals crossed valleys, mountains, and uneven terrain, while maintaining gradients so small that errors of only a few centimeters could have disrupted water flow. Today, engineers use GPS, laser surveying equipment, and digital terrain models to maintain such precision, but the Romans had none of these tools. Instead, they relied on simple instruments, visual observations, and mathematical surveying methods. Many researchers consider the hydraulic network itself to be one of the greatest unsolved engineering achievements at Las Medullas. The question remains simple yet profound. How did Roman surveyors maintain accuracy across such enormous distances without modern measurement technology? Las Medulas was not a small mine. Researchers estimate that more than 100 million cubic meters of rock and sediment may have been displaced during mining operations. To understand the scale, consider that the Great Pyramid of Giza contains roughly 2.6 million cubic meters of stone. Las Medulas involved moving dozens of times that volume. The operation continued for nearly 2 centuries, during which thousands of workers, engineers, surveyors, labourers and support personnel had to be supplied with food, tools, timber and equipment. The logistics alone rivaled those of major military campaigns, yet surprisingly few detailed records survive. The physical evidence demonstrates remarkable organisational capability, but the management systems behind the project remain largely unknown. Beneath Las Medulas lies an intricate network of tunnels carved directly into the mountains. Many passages appear strategically positioned rather than randomly excavated. Some tunnels seem designed to weaken structural support points, directing collapse towards specific areas rich in gold-bearing sediment. Modern mining engineers frequently use computer simulations to model stress distribution within rock masses, but Roman engineers relied entirely on observation and experience. Even more remarkable, many collapses appear to have occurred exactly where intended. This suggests a practical understanding of geological behaviour far more sophisticated than traditionally assumed. Whether this knowledge was based on centuries of experimentation or on engineering principles now lost remains a matter of debate. Of all the technological puzzles at Las Medulas, none may be more fascinating than what happened after the mountains were destroyed. Finding gold is one challenge. Separating microscopic gold particles from millions of tons of mud, sand, gravel and rock is another. This is where Roman engineering enters truly mysterious territory. Excavations have revealed evidence of extensive washing systems, settling basins, channels, reservoirs and hydraulic sorting structures. The Romans appear to have used flowing water to separate materials according to density. Gold has a density of approximately 19.3 grams per cubic centimetre, while quartz averages around 2.65 and most surrounding sediments are even lighter. This difference allows gold particles to settle while lighter material is carried away. The principle sounds simple, but the execution is not. Modern mineral processing facilities carefully calculate water velocity, turbulence, particle size distribution, settling rates, channel geometry, and flow duration. Even small variations can dramatically reduce recovery efficiency. Yet Las Medulas produced extraordinary quantities of gold. Historical estimates suggest annual production may have reached several thousand kilograms, and some historians estimate that the region supplied tens of thousands of kilograms of gold to the Roman Empire over its operational lifetime. This raises a remarkable question. How efficient were Roman separation systems? The surviving channels indicate that water flow was deliberately controlled through multiple stages. Larger debris was removed first, while finer materials passed through additional washing areas where heavier particles concentrated. Some researchers compare the process to a primitive industrial ore processing plant. What remains uncertain is how Roman engineers optimized these systems. There were no fluid dynamics equations, no modern mineral processing models, and no laboratory measurements. Yet the results suggest an impressive understanding of hydraulic behavior developed entirely through empirical observation. Many archaeologists argue that the greatest lost technology of Las Medulas may not be the mountain collapse system but the knowledge of large-scale gold recovery itself. The machines disappeared, the formulas vanished, and the expertise died with the people who developed it. Modern industry depends on engines, but Las Medulas depended on gravity. Roman engineers effectively transformed elevated reservoirs into massive energy storage systems. Water collected in high-altitude reservoirs contained gravitational potential energy, and when released, that energy became a powerful industrial tool capable of transporting sediment, eroding rock, driving separation systems, and triggering mountain collapses. In many respects, Las Medulas functioned like a giant hydraulic machine. The difference is that the machine was the landscape itself. Few ancient projects demonstrate such large-scale exploitation of natural energy sources. What do you think? Were the engineers of Las Medulas simply masters of trial and error, or did they possess a level of hydraulic and mining knowledge far more advanced than history has traditionally recognized? Let us know your thoughts in the comments below. The southwestern coast of Kerala, India, is home to a quiet archaeological site that may conceal the remains of one of the most important ports of the ancient world. Beneath layers of tropical soil, archaeologists uncovered evidence of a city connected to Rome, Egypt, Arabia, and Southeast Asia nearly 2,000 years ago. Yet despite years of excavation, many of its most advanced technologies remain poorly understood. If Patanam is indeed the legendary port of Maziris described in ancient texts, it raises an extraordinary question. How did a city at the edge of the Indian Ocean develop engineering, manufacturing, and trade systems sophisticated enough to rival some of the greatest commercial centers of antiquity? Systematic excavations began in 2007 under the Patanam Archaeological Research Project. What initially appeared to be a modest settlement soon revealed an astonishing quantity of artifacts. More than 100,000 artifacts have been recovered, including Roman amphorae, Mediterranean ceramics, glass beads, semi-precious stones, metal objects, brick structures, ring wells, and evidence of industrial activity. Radiocarbon dating places major occupation between approximately 1000 BCE and 500 CE. The discoveries immediately attracted international attention because they matched descriptions of Maziris, the famous port mentioned in the Periplus of the Erythraean Sea and Roman trade records. Yet every new discovery seemed to create even more mysteries. Ancient Roman sources describe Maziris as one of the busiest ports involved in trade between the Roman Empire and India. Roman historian Pliny the Elder complained that trade with India drained vast quantities of Roman gold. Some estimates suggest that millions of sesterces flowed eastward every year through Indian Ocean commerce. If Patanam was truly Maziris, then enormous amounts of cargo once passed through this region. Excavations have uncovered imported amphorae used for transporting wine and olive oil. Fragments of Mediterranean pottery have been identified. Beads, gemstones, and luxury goods indicate connections extending thousands of kilometers across the ancient world. Yet a major problem remains. Archaeologists have still not located the massive harbour infrastructure one would expect from a port of such importance. Where were the docks? Where were the shipyards? Where were the warehouses capable of handling international trade on such a scale? Some researchers suspect that centuries of river migration, flooding, and coastal change buried or destroyed the harbour. Others suggest that portions of the ancient port may now lie underwater. The paradox remains unresolved. Evidence of global commerce is abundant, but the infrastructure that made it possible remains largely invisible. One of the most surprising discoveries at Patanam involves water technology. Archaeologists uncovered numerous ring wells, drainage systems, brick-lined channels, and carefully designed water control structures. At first glance, these features appear simple. In reality, they reveal remarkable engineering knowledge. The region receives more than 3,000 millimeters of annual rainfall in some years, and heavy monsoon flooding would have posed constant threats to urban life. Maintaining stable water supplies while simultaneously preventing flooding required sophisticated planning. Many ring wells consist of stacked terracotta cylinders placed with impressive precision, and some descend several meters below ground level. Researchers continue debating their exact purpose. Were they water wells, filtration systems, sanitation structures, flood control mechanisms, or possibly all of the above? What makes the mystery even more intriguing is that similar technologies appeared centuries earlier in the Indus Valley civilization. Sites such as Mohenjo-Daro and Harappa possessed advanced drainage systems around 4,000 years ago. Did knowledge survive across millennia through cultural transmission, or did different societies independently develop similar engineering solutions? No definitive answer exists. Pattanam participated in one of history's largest maritime trade networks. Goods moved between India, Egypt, the Roman Empire, Arabia, East Africa, and Southeast Asia. The distances involved were enormous. The voyage from the Red Sea to India's west coast exceeded 4,000 kilometers. Ancient sailors lacked GPS, radar, satellites, and modern navigation systems, yet they crossed open ocean with remarkable consistency. Historians believe navigators exploited seasonal monsoon winds. Greek sailor Hippolus is traditionally credited with recognizing these wind patterns during the 1st century BCE, although Indian sailors likely understood them much earlier. Even so, understanding monsoons alone does not fully explain the precision required. Successful voyages demanded detailed knowledge of currents, weather patterns, ship performance, cargo distribution, and celestial navigation. Almost none of the technical manuals behind this knowledge survive. The trade system existed, but the science that powered it has largely vanished. Among all of Pattanam's technological puzzles, none may be more fascinating than its glass beads. Thousands upon thousands of beads have been recovered from excavations. Some measure only a few millimeters in diameter, while others display colors, shapes, and manufacturing qualities that required extraordinary technical control. To modern observers, a tiny bead may seem insignificant. In reality, producing high-quality glass beads in antiquity was an exceptionally complex technological achievement. Glass production requires temperatures often exceeding 1,000 degrees Celsius. Craftsmen needed precise control over furnace conditions, fuel quality, airflow, cooling rates, and chemical composition. Even small variations could ruin an entire production batch. Chemical analyses indicate that some beads originated from distant regions, while others may have been manufactured locally. This raises a major archaeological mystery. If local production occurred, where are the industrial facilities responsible? Despite extensive excavations, evidence for large-scale bead manufacturing workshops remains surprisingly limited. Yet the quantity of beads suggests organized production rather than occasional craft activity. The technological challenges become even more impressive when examined closely. Ancient artisans needed to control silica content, alkali levels, and coloring agents. Certain shades of blue required copper compounds, while green glass often depended on iron impurities. Other colors demanded complex chemical recipes discovered through generations of experimentation. Without thermometers, laboratory instruments, or written chemical textbooks, ancient craftsmen somehow mastered processes involving molecular transformations inside high-temperature furnaces. Experimental archaeologists attempting to reproduce ancient glass technologies have discovered that success often depends on subtle variables that are difficult to control even today. A slight change in furnace atmosphere can alter color, a minor temperature fluctuation can affect transparency, and tiny differences in cooling rates can cause cracking. Yet the beads found at Pattanam demonstrate remarkable consistency. This has led some researchers to propose that highly specialized artisans operated within organized production networks, supported by accumulated technical knowledge passed from generation to generation. The artifacts survive, but the manufacturing secrets do not. Perhaps the greatest mystery is not how the beads were traded, but how the knowledge required to create them disappeared so completely. The discoveries at Patanam reveal far more than isolated craftsmanship. They point toward a highly organized urban economy. Imported ceramics, standardized artifacts, storage facilities, manufacturing debris, and trade goods suggest coordinated systems involving procurement, production, quality control, transportation, and distribution. Modern industrial centers depend on logistics networks, and ancient Patanam appears to have done the same. Yet, unlike modern cities, almost no written documentation survives. No business records explain inventory management, no manuals describe manufacturing procedures, and no administrative archives reveal how trade was regulated. The archaeological evidence demonstrates organization, but the organizational methods remain hidden. Perhaps the greatest mystery is how such an important center vanished. Historical and geological studies suggest that major flooding events transformed Kerala's river systems over time. One commonly discussed event occurred in 1341 CE, when catastrophic flooding may have altered channels, reshaped coastlines, and changed maritime access routes. If major waterways shifted, a harbour dependent on those waterways could have become unusable almost overnight. Trade routes would relocate, merchants would follow new ports, and economic activity would collapse. Over generations, memory itself could disappear. A city that once connected continents could become little more than a forgotten landscape beneath tropical vegetation. How much technological knowledge did the people of Patanam possess, and how much of it has been lost to history forever? The island of Anglesey in northern Wales is home to a mountain stained red, orange, yellow, and purple by copper minerals. Today it looks almost alien. Yet thousands of years ago, long before geological surveys, chemical laboratories, or mining engineering existed, people were already extracting valuable metal from this landscape. The greatest mystery is not that they found copper. The mystery is how they knew exactly where to look. Evidence of ancient mining at Paris Mountain emerged through archaeological investigations, mineral studies, and discoveries of prehistoric and Roman period activity across the region. Modern research revealed that this unusual mountain was one of the richest copper deposits ever exploited in Britain. But every new discovery has raised a deeper question about the knowledge possessed by its earliest miners. Paris Mountain contains one of the largest concentrations of copper-bearing minerals in Britain. Modern geological surveys have identified extensive deposits of copper sulfides, including chalcopyrite and other mineralized veins spread throughout the mountain. During the 18th century, the site became one of the world's most productive copper mines, producing hundreds of thousands of tons of ore. What puzzles archaeologists is that evidence suggests people were exploiting this resource thousands of years earlier. Copper was one of the most important strategic materials of the Bronze Age. To produce bronze, ancient societies needed copper and tin. Without copper, there could be no bronze tools, weapons, agricultural equipment, or prestige objects. Yet Bronze Age communities lacked maps, drilling rigs, geochemical analysis, and modern mining equipment. Despite these limitations, they somehow identified one of Britain's richest copper sources. The achievement becomes even more impressive when compared with many modern mineral discoveries, which often require satellite imagery, airborne surveys, and extensive drilling programs before economically valuable deposits can be confirmed. Ancient miners accomplished the first step without any of these technologies. How? No one knows. This may be the most fascinating unanswered question at Paris Mountain. Finding metal underground is extremely difficult. Modern mining companies spend millions of dollars searching for ore deposits. exploration teams use magnetic surveys, electrical resistivity measurements, seismic imaging, geochemical sampling, and three-dimensional geological modelling. Even with these technologies, many exploration projects fail, yet ancient miners repeatedly located productive ore bodies. At Paris Mountain, the challenge would have been even greater because not every part of the mountain contains equally valuable mineral concentrations. Identifying the richest zones required selecting specific locations from a complex geological environment. Some researchers believe ancient prospectors relied on visible clues. The mountain's unusual colours may have played an important role. Copper minerals often produce striking blue, green, red, and yellow staining on exposed rock surfaces. Groundwater moving through mineralized zones can also alter surrounding soils and vegetation. But there is a problem with this explanation. Visible surface staining does not always indicate the richest deposits below. Modern geologists know that surface indicators can be misleading. Many promising-looking locations contain little valuable ore, while some major deposits show almost no obvious signs at the surface. Yet ancient miners often achieved remarkable success. This has led some researchers to propose that generations of observation created a sophisticated practical understanding of geology long before geology became a science. Imagine hundreds of years of accumulated experience. One generation notices unusual rock colours, the next generation learns which colours correlate with better ore, and later generations learn how groundwater behaves near mineralised zones. Eventually, a body of knowledge emerges that allows experienced prospectors to identify promising locations with surprising accuracy. No written manuals survive and no technical instructions exist, but the results suggest a level of empirical geological knowledge that may have taken centuries to develop. The situation is similar to other ancient mining centres such as the copper mines of Great Orme in Wales, the Rio Tinto mining district in Spain, and the Mitterberg mines in Austria. Across Europe, prehistoric miners repeatedly found valuable deposits that modern geologists later confirmed were exceptionally rich. The knowledge behind those discoveries remains largely invisible. Perhaps the greatest lost technology was not a machine. Perhaps it was an understanding of the landscape itself. Another problem facing researchers is that much of the ancient mine has disappeared. Centuries of later mining dramatically altered the mountain. Massive industrial excavations destroyed large portions of earlier workings. As a result, archaeologists are attempting to reconstruct a prehistoric mining system that no longer fully exists. Evidence suggests that ancient miners may have created extensive networks of pits, trenches, and underground passages. But how large were these systems? How deep did they extend? How were they organized? No one can answer with certainty. It is possible that some of the most impressive engineering achievements were destroyed before modern archaeology could document them. In many ways, researchers are investigating a shadow of the original mine. Before explosives were invented, ancient miners faced a serious challenge. Rock is hard and copper ore is trapped inside it. One of the most effective prehistoric solutions was a technique known as fire setting. The process sounds simple. Large fires were built against rock surfaces, and after prolonged heating, cold water was applied. The sudden temperature change caused fractures to develop, allowing miners to break the rock apart. In reality, this was a sophisticated engineering process. Experiments have shown that fire setting can generate temperatures approaching several hundred degrees Celsius and dramatically weaken certain rock types. Success depended on understanding fuel quality, airflow, rock composition, heating duration, and cooling methods. Poor execution wasted enormous amounts of labor and fuel, while effective execution could transform solid rock into workable material. The miners of Paris Mountain appear to have mastered this technique without scientific instruments, thermometers, or engineering textbooks. Their knowledge existed entirely through experience. Finding ore was only the beginning. Producing usable metal required far greater expertise. Copper smelting generally requires temperatures exceeding 1,000 degrees Celsius. Ancient furnaces had to maintain high heat while carefully controlling airflow and fuel consumption. Even slight variations could affect metal quality. Archaeological evidence from Bronze Age Europe demonstrates that ancient metallurgists achieved surprisingly consistent results despite lacking modern measuring devices. This consistency suggests the existence of highly refined production methods. Workers understood furnace design, charcoal quality or preparation, and temperature management. Yet almost none of this technical knowledge was ever written down. The metal survived. The instructions did not. One of the most remarkable features of Paris Mountain is its appearance. The mountain's colours are created by complex chemical interactions involving copper, iron, sulfur, oxygen, and water. Oxidation reactions produce vivid mineral deposits across the landscape, while acidic drainage generated by sulfide minerals can dramatically alter the surrounding environment. Today, scientists use laboratory analysis to understand these processes. Ancient miners had no such tools, yet they may have recognized practical relationships between color, mineral composition, and ore quality. If true, they were effectively practicing a form of field geochemistry thousands of years before modern chemistry existed. Not through equations, not through laboratories, but through observation. How were ancient people able to identify one of the richest copper deposits in Britain with a level of accuracy so remarkable that it continues to astonish us even in the age of modern geology? Eastern Spain, overlooking the valley of the Tagus River, lies the ruins of a city that challenges one of history's most accepted assumptions. For generations, historians described the centuries following the fall of the Western Roman Empire as a technological decline. Roads deteriorated, cities shrank, and engineering knowledge supposedly faded across much of Europe. Yet, in the late 6th century, a new city suddenly appeared. Not a settlement that evolved over centuries, not a Roman city adapted by later rulers, but an entirely new city, designed, planned, and constructed from scratch. Its name was Rekopolis. More than 1,400 years later, archaeologists are still trying to understand how its builders achieved engineering feats that seem surprisingly advanced for their time. And among all its mysteries, none may be more intriguing than evidence of a sophisticated royal mint whose level of organization continues to puzzle researchers today. The ruins of Rekopolis are located near modern Zorita de los Canes in Guadalajara province, Spain. Although local inhabitants had long known about the site, systematic archaeological excavations began during the 20th century and expanded significantly after the 1940s. What researchers uncovered was astonishing. Beneath centuries of soil lay one of the best preserved Visigothic cities ever discovered, covering approximately 30 hectares and containing streets, monumental buildings, workshops, defensive walls, religious structures, and evidence of industrial production. Unlike many ancient sites, Rekopolis was not inherited from Rome. It was built around 578 AD by the Visigothic king Leovigild and named after his son Recared. This fact alone makes it extraordinary. Very few early medieval cities in Europe can be linked to a specific founding event with such confidence. Most ancient cities grew gradually. Rome expanded over centuries. Athens evolved through countless construction phases. Even Constantinople developed from earlier settlements. Rekopolis followed a completely different pattern. Archaeological surveys suggest that planners designed major sections of the city before large-scale construction began. Wide streets connected administrative buildings, religious centres, residential districts, and industrial zones. This level of planning required surveying techniques, measurement systems, and organisational capabilities rarely associated with 6th century Europe. Modern engineers understand that creating an urban plan requires accurate assessment of slopes, drainage, visibility, transportation routes, and building loads. Yet no technical manuals survive, no architectural drawings have been found, and no written instructions explain how the planners transformed a rocky landscape into a functioning city. The city exists, but the engineering knowledge behind it largely does not. Building Rekopolis required more than constructing walls. The terrain itself had to be modified. Archaeological investigations reveal extensive levelling operations across portions of the site. Large quantities of earth and stone were moved to create stable construction platforms. Today, moving thousands of cubic meters of material requires heavy machinery, laser-guided surveys, and geotechnical analysis. The builders of Rekopolis possessed none of those technologies. Yet many foundations remained stable for more than 14 centuries. This raises an important question. How did the engineers determine where structures could safely stand? How did they evaluate soil stability? How did they prevent differential settlement that could crack walls and collapse buildings? Researchers can observe the results, but the methods remain uncertain. Every successful city depends on water. Without reliable water systems, urban life becomes impossible. Excavations at Rekopolis have revealed evidence of carefully planned hydraulic infrastructure. Channels, drainage features, and water control elements indicate that engineers understood the importance of directing water away from critical structures. At first glance, this may seem simple. In reality, hydraulic engineering is one of the most difficult challenges in urban design. A drainage channel that is too steep erodes itself, while a channel that is too shallow becomes blocked. A small error in gradient can render an entire system ineffective. Roman engineers mastered these principles through centuries of experimentation. What remains unclear is how much of that knowledge survived among the Visigoths. Some researchers argue that Rekopolis preserved important elements of Roman hydraulic expertise, while others suggest that local engineers adapted inherited techniques and developed new solutions. Either way, the city demonstrates a practical understanding of water management far beyond what many historians once expected. The most impressive structure discovered at Rekopolis is the Royal Palace complex. The building occupied a commanding position overlooking the city and served as the political centre of Visigothic authority. Its size alone is remarkable. The construction required massive quantities of stone, timber, mortar, roofing materials, and skilled labour. To understand the challenge, consider a comparison. The palace was built nearly a century before the construction of many famous early medieval European centres, often associated with political power. Yet it displays evidence of advanced planning, monumental architecture, and coordinated construction. The logistics are difficult to comprehend. Workers needed food, builders needed tools, materials had to arrive according to schedule, and construction phases had to be coordinated. Without efficient management, the project could not have succeeded. The palace therefore represents not only an architectural achievement, but also an organisational one. One of the greatest mysteries surrounding Rekopolis concerns the source of its technical expertise. Where did the knowledge come from? Several theories exist. Some historians believe Roman engineers or their descendants continued working long after the empire's political collapse. Others point toward Byzantine influences. A third possibility is that Visigothic builders independently preserved and refined practical engineering traditions. The problem is that evidence supports all three possibilities to varying degrees. The city contains features that resemble Roman urban planning. Other elements appear uniquely Visigothic, while still others have parallels elsewhere in the Mediterranean world. Rather than answering questions, Rekopolis creates new ones. It may represent a technological bridge connecting the ancient world to the medieval era. Of all the technological puzzles at Rekopolis, none may be more fascinating than its mint. Archaeologists have discovered evidence indicating that the city served as one of the most important coin-producing centres in the Visigothic kingdom. At first glance, minting coins may seem straightforward. It was anything but. Producing high-quality currency required extraordinary precision. Metal had to be refined, alloys had to be controlled, coin blanks had to be manufactured with consistent dimensions, dies had to be engraved with remarkable accuracy, and weight standards had to be maintained. Every stage demanded technical expertise. The challenge becomes even more impressive when viewed scientifically. A deviation of only a fraction of a gram could undermine confidence in a currency system. Modern mints rely on automated scales capable of measuring differences measured in thousandths of a gram. Visigothic mint workers had no such equipment, yet surviving coins display remarkable consistency. Gold tremisses produced in Visigothic Spain often conform closely to expected weight standards, despite being manufactured entirely by hand. This raises a profound question. How did mint officials achieve such precision? No surviving documents explain their measurement systems. No technical manuals describe their procedures. No detailed records reveal how quality control was enforced. Researchers can analyze the coins themselves, but the production process remains largely invisible. The mystery deepens further. Coin production required reliable access to precious metals. Gold sources had to be identified, materials had to be transported securely, impurities had to be removed, and counterfeiting had to be prevented. All of these activities required administrative systems operating at a surprisingly sophisticated level. The mint, therefore, reveals something larger than metallurgy. It reveals the existence of a highly organized state capable of controlling resources, enforcing standards, and maintaining economic trust across large territories. Yet the mechanisms behind that system remain poorly understood. In many ways, the Mint of Rekopolis resembles another famous technological puzzle, the Antikythera mechanism. Both demonstrate expertise that appears unexpectedly advanced. Both reveal knowledge that was clearly real, and both leave behind far fewer explanations than modern researchers would like. Recent excavations suggest that Rekopolis was more than a royal residence. Evidence of workshops points to active industries such as metalworking, glass production, and construction materials. These activities required skilled workers and technical knowledge, raising questions about how such expertise was preserved and passed down during a period often seen as technologically stagnant. Just northwest of Seville, Spain, lies a Roman city where engineers solved problems that still challenge urban planners today. Beneath its ruined streets, giant amphitheatre, and magnificent mosaics lies evidence of technological knowledge that may have been centuries ahead of its time. Although local inhabitants had long known about the ruins, systematic archaeological investigations began during the 18th and 19th centuries. Excavations gradually revealed an enormous Roman city founded in 206 BC and expanded dramatically under Emperor Hadrian during the 2nd century AD. What archaeologists uncovered was not merely another Roman settlement, it was one of the most sophisticated urban engineering projects in the Western Roman Empire. One of Italica's first mysteries appears before examining a single building. the city seems far too large for its population. Archaeological estimates suggest that Italica may have housed between 8,000 and 15,000 inhabitants during its peak, yet many of its public works were designed on a scale that appears suitable for a much larger urban centre. Its streets were unusually wide, residential districts occupied vast areas, and public spaces were monumental. Most striking of all was an amphitheatre capable of accommodating approximately 25,000 spectators. To understand how unusual this was, consider that many modern sports arenas are designed to serve populations significantly larger than the city itself. Italica appears to have followed a similar logic nearly 2,000 years ago. Why? Some historians believe Emperor Hadrian intended to transform his birthplace into a major administrative centre of Roman Hispania. Others suggest the city represented an ambitious political statement designed to rival Rome's most prestigious provincial capitals. Yet archaeological surveys indicate that portions of the planned expansion were never fully completed. Entire sections appear to have been prepared for development but remained underutilised. The result is a city that looks like a grand vision, frozen midway through execution. Roman engineers were famous for aqueducts, but Italica presents unusual questions even by Roman standards. The city required enormous quantities of water. Bath complexes, fountains, workshops, households, gardens, and public facilities all depended on a continuous supply. Archaeologists have uncovered reservoirs, distribution channels, underground conduits, and sophisticated drainage systems. Together, they formed an integrated hydraulic network stretching throughout the city. Modern hydraulic modelling suggests that maintaining stable water flow across such a network would have required careful calculations involving pressure, elevation, and storage capacity. The mystery is that important portions of the system have not survived. Researchers can identify the components, but reconstructing exactly how the entire network functioned remains difficult. Some engineers have proposed that Italica employed intermediate storage tanks that helped regulate pressure fluctuations, a principle still used in modern municipal water systems. If true, the city's designers possessed a practical understanding of hydraulic behaviour far more advanced than many assume for the ancient world. Ancient cities often suffered from flooding, sewage accumulation, and stagnant water. Italica appears to have solved these problems remarkably well. Beneath the streets lies a network of underground drains whose gradients were carefully calculated to maintain flow while minimizing erosion. What makes this achievement remarkable is the precision required. A drainage tunnel extending hundreds of meters can fail if the slope is too steep or too shallow. Excessive gradients increase erosion, while insufficient gradients allow sediment to accumulate. Yet many sections of Italica's drainage infrastructure remained functional for centuries. The question is how Roman surveyors achieved such accuracy. There were no laser levels, no satellite positioning systems, and no digital mapping software. The primary surveying instruments available were simple optical devices such as the Groma and chorobates. Despite these limitations, the resulting infrastructure demonstrates a level of precision that continues to impress modern engineers. Recent studies of Roman urban planning have revealed that many cities were designed with environmental factors in mind. Italica may represent one of the clearest examples. The orientation of streets appears to encourage airflow through residential districts, while certain building layouts may have reduced solar heat accumulation during the hottest months of the year. Southern Spain regularly experiences summer temperatures exceeding 40 degrees Celsius, making heat management essential for urban life. Computer simulations performed on comparable Roman cities have demonstrated that street orientation alone can significantly influence local temperature conditions. Even small changes in airflow can reduce thermal stress across densely populated districts. If Italica's layout intentionally exploited prevailing winds from the Guadalquivir Valley, its planners may have been applying principles similar to those used in modern climate-responsive urban design. The question remains whether this knowledge resulted from formal engineering theory or centuries of accumulated practical experience. Among all of Italica's technological puzzles, none may be more astonishing than its mosaics. At first glance, they appear purely artistic, but closer examination reveals something very different. Many of Italica's mosaic floors were constructed from hundreds of thousands of individual tesserae, small pieces of stone, marble, ceramic, and coloured materials carefully cut and positioned by hand. The House of the Planetarium contains one of the most famous examples, its design depicting celestial symbolism through geometric arrangements of extraordinary complexity. What makes these mosaics remarkable is not merely their beauty, but their precision. Modern measurements show that many geometric patterns maintain alignment across large floor surfaces with surprisingly little deviation. Symmetrical figures remain balanced despite being assembled from countless individual components. Imagine constructing a giant image covering dozens of square meters while using pieces sometimes measuring only a few millimeters across. Now imagine doing so without lasers, digital templates, computer-aided design software, or modern measuring equipment. The challenge becomes even greater when considering optical correction. Researchers studying Roman mosaics have discovered that some designs appear to compensate for viewing angles and spatial distortions. Certain geometric arrangements look perfectly symmetrical to observers despite minor adjustments hidden within the pattern itself. This suggests that mosaic craftsmen understood visual perception at a sophisticated level. The mathematical planning required is extraordinary. Before placing a single tessera, artisans needed to calculate proportions, establish reference grids, maintain alignment, distribute colors, and coordinate thousands of individual placements. One mistake could disrupt an entire section, yet many Italica mosaics display a consistency that rivals modern architectural decoration. The mystery deepens when examining durability. Nearly 2,000 years later, numerous mosaic sections remain recognizable despite earthquakes, weathering, soil pressure, human activity, and centuries of neglect. The survival of these floors depended not only on artistic skill but also on engineering. Roman builders typically constructed mosaics atop multiple foundation layers. These layers distributed loads, reduced cracking, controlled moisture, and stabilized the surface. What remains uncertain is how craftsmen determined the optimal thickness and composition for these layers. No surviving technical manuals explain the process in sufficient detail. The finished masterpieces remain, but the engineering knowledge behind them has largely vanished. In many ways, Italica's mosaics resemble the Antikythera mechanism. Both reveal levels of sophistication that exceed what many people expect from the ancient world. Both demonstrate practical knowledge that was clearly real, and both leave modern researchers asking the same question: how much technical expertise has been lost? Italica's amphitheatre ranks among the largest in the Roman Empire. Its structure required massive earthworks, retaining systems, circulation corridors, stairways, foundations, and load-bearing walls. Thousands of spectators could enter, move through and exit the structure efficiently. Modern stadium engineers recognize this as a highly complex design challenge in which crowd movement, structural stability, visibility, and safety must all be balanced simultaneously. Yet Roman engineers achieved these goals nearly 2 millennia ago. Even more remarkable is the structure's longevity. Although partially ruined, significant portions remain standing after centuries of environmental stress. The original builders succeeded in creating a structure whose fundamental engineering principles continue to function long after the empire that built it disappeared. The banks of the Narmada River in central India are home to Maheshwar, a settlement whose ancient craftsmen may have mastered manufacturing techniques that remain surprisingly difficult to explain. Long before factories, thermometers, or scientific laboratories existed, they produced ceramics of remarkable consistency, engineered complex trade networks, and left behind evidence of technological knowledge that seems far ahead of what many would expect from a Bronze Age community. The archaeological significance of Maheshwar became clear during excavations conducted in the mid-20th century, particularly alongside investigations at nearby Navdatoli across the Narmada River. Archaeologists uncovered houses, workshops, storage facilities, pottery, copper artifacts, stone tools, and evidence of long-term settlement dating roughly between 1800 and 1400 BCE. What initially appeared to be a typical Chalcolithic settlement soon revealed a series of technological mysteries that continue to attract scientific attention today. Among all the discoveries made at Maheshwar, none may be more intriguing than its pottery. Thousands of ceramic fragments have been recovered, many belonging to a distinctive category known as black-on-red ware. At first glance, these vessels appear decorative, but closer examination reveals something far more impressive. The pottery displays consistent coloration, carefully controlled firing patterns, uniform wall thickness, and geometric designs executed with remarkable precision. These characteristics suggest that the artisans were not simply making containers, they were operating a manufacturing system capable of producing highly standardized results. That raises a difficult question. How were Bronze Age potters able to repeatedly achieve such consistency without modern instruments? Modern ceramic production relies heavily on temperature monitoring. Industrial kilns often operate between 900 and 1200 degrees Celsius, depending on the desired material properties, and small variations can dramatically alter color, strength, porosity, and durability. The potters of Maheshwar possessed no thermometers, yet the evidence suggests they repeatedly controlled firing environments with surprising accuracy. To create the characteristic black and red coloration found on many vessels, potters had to manipulate oxygen levels inside the kiln. Different parts of a vessel were exposed to different atmospheric conditions during firing, a process that requires precise control of airflow and combustion. Experimental archaeologists attempting to recreate ancient pottery have discovered that achieving these effects consistently is far more complicated than it appears. Slight differences in fuel moisture, kiln construction, clay composition, or firing duration can completely change the final result. Even experienced modern experimental potters often require multiple attempts before reproducing ancient firing patterns successfully. The mystery becomes even more fascinating when one considers scale. The pottery recovered from Maheshwar was not limited to a handful of ceremonial objects. Archaeologists have found evidence of large-scale production extending across generations. This suggests that the knowledge was not accidental, it was systematic. Someone understood the process well enough to teach it repeatedly over centuries. Yet no written instructions survive. No technical manuals exist. No records explain how firing temperatures were estimated, how kiln atmospheres were controlled, or how production standards were maintained. The product survived, but the knowledge disappeared. The kiln itself may be one of Maheshwar's greatest unsolved technological puzzles. Ancient kilns appear simple compared to modern industrial furnaces, but in reality they function as highly complex thermal systems. Temperature distribution inside a kiln depends on airflow, fuel arrangement, chamber geometry, insulation properties, and combustion efficiency. Modern engineers use mathematical models and computer simulations to study these variables, while ancient potters relied entirely on experience. Yet evidence from Maheshwar suggests that they consistently produced results that would have required careful thermal management. Some researchers compare this phenomenon to other ancient technological achievements. Roman engineers produced concrete capable of surviving nearly 2,000 years in marine environments. The builders of the Egyptian pyramids transported multi-ton stone blocks with astonishing precision. The creators of the Antikythera mechanism built a machine whose complexity would not be matched for centuries. Maheshwar's potters belong to the same broader pattern, demonstrating that practical engineering knowledge often developed far beyond what surviving written records suggest. Another question concerns production efficiency. The quantity of pottery discovered indicates that manufacturing was not an occasional activity, it was a major economic enterprise. Large communities require enormous numbers of ceramic vessels for storing grain, transporting liquids, cooking food, and supporting trade. To satisfy such demand, artisans needed reliable systems for sourcing clay, preparing raw materials, controlling quality, organizing labor, and distributing finished products. These processes resemble the principles of industrial production, yet Maheshwar existed more than 3,000 years before the Industrial Revolution. How were production standards maintained? How were apprentices trained? How were defective products identified? Archaeology provides fragments of evidence but few definitive answers, and the organizational systems behind the industry remain largely invisible. Maheshwar belonged to the Chalcolithic period, an era defined by the growing use of copper. Excavations have uncovered copper tools, ornaments, and other metal artifacts. The problem is geographical. The immediate region around Maheshwar contains limited major copper resources, suggesting that raw materials traveled significant distances before reaching local craftsmen. Some possible sources lie hundreds of kilometers away in regions such as Rajasthan. Transporting metal over such distances would have required extensive trade networks. For comparison, moving bulk materials across hundreds of kilometers in the ancient world demanded substantial logistical organization, coordination, and economic planning. Yet very little direct evidence survives explaining how these networks functioned. The artifacts indicate long-distance exchange, but the mechanisms behind it remain largely hidden. Archaeologists have also recovered beads made from semi-precious stones, including carnelian and agate. Many contain tiny perforations drilled through extremely hard materials, and the precision is remarkable. Carnelian has a hardness approaching 7 on the Mohs scale, making it significantly more difficult to work than ordinary stone. Creating narrow, centered holes through such material without causing fractures requires considerable skill. Researchers studying ancient bead production have demonstrated that even with reconstructed traditional tools, the process can be labor-intensive and technically demanding. The surviving beads raise an obvious question. What drilling techniques allowed ancient craftsmen to achieve such consistent results? The finished products survive, but the manufacturing methods remain uncertain. Maheshwar occupied a strategic position along the Narmada River, one of India's most important waterways. Many archaeologists believe the river functioned as a transportation corridor linking distant regions. Artifacts recovered from the site suggest interactions extending far beyond the immediate settlement. If the Narmada served as a major trade route, Maheshwar may have occupied a role similar to other ancient riverine centers around the world. The Nile supported Egyptian civilization. The Tigris and Euphrates sustained Mesopotamia. The Indus connected major urban centers across Northwest and South Asia. Could the Narmada have played a comparable role on a regional scale? The evidence points in that direction, but the full extent of the network remains unknown. Were the craftsmen of Maheshwar simply masters of knowledge accumulated through generations of experience? Or did they possess a deeper understanding of materials, heat, and manufacturing techniques than modern archaeology is currently capable of recognizing? Towering above the Vale of Clwyd in northern Wales, Denbigh Castle should not exist in the form we see today. Built on an uneven limestone ridge more than 700 years ago, its massive gatehouse still dominates the landscape despite wars, weather, earthquakes, and centuries of neglect. Yet the greatest mystery is not why the castle was built. It is how medieval engineers achieved such a feat of construction without modern surveying equipment, structural calculations, or mechanical machinery. The ruins have never truly been lost. Standing above the town of Denbigh, the castle has remained visible since its construction began in 1282 under the orders of Henry de Lacy, Earl of Lincoln, following King Edward's conquest of Wales. However, modern archaeological investigations during the 19th and 20th centuries revealed something unexpected. Beneath the familiar ruins lay evidence of an extraordinarily sophisticated engineering project whose technical complexity rivaled some of the most advanced military architecture in medieval Europe. What initially appeared to be another ruined fortress gradually emerged as one of the most ambitious construction programs ever attempted in Wales. Most medieval castles were built on hills because elevation provided defensive advantages, but Denbigh's builders faced a more difficult challenge. The limestone ridge chosen for construction was not a flat platform. It consisted of irregular rock formations, natural fractures, varying elevations, and unstable sections that would have complicated any large-scale building project. Modern engineers typically begin such projects with geological surveys, computer models, and structural simulations, yet medieval builders possessed none of these tools. Somehow, they created foundations capable of supporting walls several meters thick and towers weighing thousands of tons. Archaeological surveys indicate that much of the castle was anchored directly into bedrock. Builders had to identify stable load-bearing points across an uneven geological surface while maintaining alignment throughout the fortress. The remarkable result is that despite centuries of deterioration, many major sections remain standing. In some locations, the foundations have shifted surprisingly little considering the immense weight they have carried for over 7 centuries. This raises an obvious question. How did 13th century builders accurately evaluate the strength of the underlying rock without modern geology? The answer remains largely unknown. Denbigh Castle was not simply a collection of walls, it was a carefully designed defensive machine. Military historians have identified overlapping fields of fire throughout the fortress, allowing archers positioned in different locations to attack the same target from multiple angles simultaneously. Dead zones where attackers could shelter were minimized, approach routes forced enemies into predictable pathways, and defensive towers provided visibility across large portions of the surrounding landscape. These principles resemble concepts found in later military engineering manuals, yet Denbigh was constructed centuries before many formal theories of battlefield geometry emerged. Similar design sophistication can be seen at Caernarfon Castle and Conwy Castle, but Denbigh exhibits unique adaptations to its challenging terrain. Whether these solutions emerge through experience, experimentation, or lost engineering knowledge remains debated. Of all Denbigh's mysteries, none is more fascinating than the Great Gatehouse. This enormous structure dominates the entire fortress. At first glance, it appears to be simply an entrance, but closer examination reveals something far more extraordinary. The gatehouse contains massive stone walls, multiple defensive chambers, upper-level rooms, passageways, stair systems, murder holes, and defensive positions integrated into a single architectural unit. Its dimensions are astonishing for the period. The The structure required thousands of tons of stone, carefully distributed across an irregular foundation, while maintaining stability over centuries. What makes this particularly mysterious is the absence of engineering documentation. No architectural blueprints survive, no construction manuals explain how the loads were calculated, and no records describe the design process. Yet the building demonstrates an impressive understanding of structural mechanics. Modern structural engineering relies on equations that calculate compressive forces, stress distribution, and load transfer. Medieval builders possessed no known mathematical framework comparable to today's methods. Nevertheless, the Great Gatehouse remains standing. Even more remarkable is the way its builders used arches and vaults. Arches are deceptively complex structures, requiring every stone to transfer force into adjacent stones while directing weight towards supporting walls. A small error in geometry can cause catastrophic failure. Experiments conducted by architectural historians have demonstrated that medieval masons often achieved tolerances far more precise than expected from supposedly primitive tools. The Great Gatehouse suggests that Denbuch's builders possessed an intuitive understanding of force distribution that rivaled practical engineering expertise. Some researchers compare this phenomenon to the construction of Gothic cathedrals such as Notre Dame in Paris, where builders successfully created enormous stone structures without modern calculations. Others point to similarities with Edward III's castles throughout Wales, often described as the most advanced military architecture in Europe during the late 13th century. Yet Denbuch's gatehouse remains unusual even within that elite group. Why was such a gigantic gatehouse necessary? Why invest so much labour and material into a single component of the fortress? Some historians believe it served as a symbol of English authority following the conquest of Wales, while others argue that it represented a defensive innovation designed to withstand increasingly sophisticated siege tactics. Neither explanation fully accounts for its scale. The gatehouse remains one of medieval Britain's most impressive and least understood engineering achievements. Every fortress faces the same problem: water. Without a reliable supply, even the strongest castle becomes vulnerable. Denbuch's elevated position created a logistical challenge because natural water sources were not easily accessible during a siege. Archaeological evidence suggests the existence of wells, cisterns, and rainwater collection systems, but many details remain uncertain. How much water could actually be stored? How were supplies protected from contamination? How long could the fortress survive under siege? These questions are difficult to answer because much of the hydraulic infrastructure has disappeared. Yet historical evidence indicates that medieval engineers often possessed surprisingly advanced knowledge of water management. Across Europe, monastic communities, castles, and fortified towns developed sophisticated drainage and storage systems centuries before modern plumbing. Denbuch may represent another example of technical knowledge that has largely vanished. One of the least appreciated mysteries is transportation. Building the castle required vast amounts of stone, timber, iron, and food, with major Edwardian castles consuming tens of thousands of tons of material. Without trucks, cranes, railways, or powered machinery, everything relied on human and animal labour. At Denby, builders managed large workforces and complex logistics with a remarkable precision, demonstrating organisational skills as impressive as the engineering itself. What do you think? Was the Great Gatehouse simply the product of generations of accumulated craftsmanship? Or did Denbuch's builders possess engineering knowledge far more advanced than historians currently recognise? Let us know your thoughts in the comments below. Southern Saudi Arabia, near modern-day Najran. Beneath the desert lies Al-Ukhdud, an ancient city whose ruins have survived for more than 15 centuries. Massive stone walls, sophisticated urban planning, mysterious inscriptions, and evidence of advanced manufacturing suggests that this was far more than a simple desert settlement. The city is famous for its connection to ancient historical accounts, but archaeologists have become increasingly fascinated by something else: the remarkable technological capabilities of the people who lived here. Many of the engineering methods that allowed Al-Ukhdud to flourish remain poorly understood today. Although local inhabitants had long known of the ruins, systematic archaeological excavations began during the 20th century. Researchers uncovered defensive walls, residential districts, workshops, inscriptions, coins, pottery, metal objects, and evidence of large-scale production activities. What emerged was not an isolated outpost, but a major urban centre, positioned along important trade routes linking southern Arabia with the wider ancient world. Each excavation revealed new evidence of technical sophistication and new mysteries. One of the first puzzles concerns construction itself. Al-Ukhdud was built largely from granite and other hardstone materials. Granite ranks approximately 6 to 7 on the Mohs hardness scale and remains one of the most difficult natural stones to shape without advanced tools. Yet many surviving structures display surprisingly regular masonry. The challenge becomes even greater when considering the environment. Average summer temperatures in the region frequently exceed 40 degrees Celsius. Transporting multi-ton stone blocks across such terrain would have required careful organization, manpower, and engineering planning. The mystery is not simply how the stones were cut. The mystery is how an entire urban landscape was constructed and maintained under such demanding environmental conditions. Comparable questions have been raised at Petra in Jordan and Madain Salih in northwestern Arabia, where ancient builders achieved astonishing stoneworking precision without modern machinery. Al-Ukhdud appears to belong to that same category of engineering mystery. No large city can survive in an arid environment without reliable water. This simple fact creates one of Al-Ukhdud's greatest unanswered questions. Ancient settlements throughout Arabia developed sophisticated methods of water collection, storage, and distribution. The famous Marib Dam in Yemen demonstrates that Arabian engineers could manipulate water resources on a massive scale more than 2,000 years ago. Al-Ukhdud almost certainly depended on comparable hydraulic knowledge, yet much of the original infrastructure has disappeared. Archaeologists know the city supported a substantial population, no agricultural activity existed nearby, and no trade caravans passed through the region. All of these activities required significant water resources. How those resources were collected, preserved, and distributed remains only partially understood. The missing hydraulic system may represent one of the greatest technological losses associated with the site. Of all Al-Ukhdud's technological puzzles, none may be more fascinating than its metallurgy. Excavations have uncovered iron tools, metal objects, manufacturing debris, workshop remains, and evidence suggesting that metalworking was an important component of the local economy. At first glance, ancient metallurgy may seem straightforward. In reality, it represents one of the most difficult technological achievements in human history. Producing usable iron requires temperatures approaching 1,150 to 1,250 degrees Celsius. Achieving such conditions without modern furnaces demands extraordinary control over airflow, fuel quality, furnace geometry, and ore selection. Even small variations can drastically alter the final product. What astonishes researchers is that ancient metal workers repeatedly achieved these results with remarkable consistency. Consider the challenge. Modern industrial furnaces use sensors, thermometers, automated airflow systems, and precise chemical monitoring. Ancient craftsmen possessed none of these tools, yet they somehow learned to recognize optimal temperatures through observation alone. They could judge furnace performance by flame colour, sound, smoke characteristics, and accumulated experience. Experimental archaeologists attempting to recreate ancient furnaces have discovered that success often depends on subtle factors invisible to inexperienced observers. A furnace that appears simple from the outside may conceal highly sophisticated engineering principles. Airflow channels must be positioned correctly, bellows must deliver air at appropriate rates, fuel must be selected carefully, and ore composition must be understood. The entire process requires extensive practical knowledge. Evidence from Unsolved suggests that its craftsmen mastered these variables well enough to sustain production over long periods. How they acquired this expertise remains unclear. Was the knowledge passed down through generations of specialists? Did master craftsmen operate secret workshops? Were technological techniques imported through trade networks connecting Arabia to neighbouring civilizations? No definitive answer exists. The mystery becomes even more intriguing when compared with other ancient metallurgical centres. Ironworkers at Meroe in Sudan, the Hittite regions of Anatolia, and certain parts of ancient India developed remarkably advanced metalworking traditions. In some cases, researchers still struggle to fully explain how ancient craftsmen achieved consistent results using relatively simple equipment. Al-Okhdud appears to belong to this same technological tradition. Its metalworkers may have possessed practical engineering knowledge far more sophisticated than historians once assumed. Metallurgy was only part of a larger production economy. Excavations reveal evidence of pottery manufacturing, stoneworking, jewellery production, and other craft activities. This raises an important question. How were these industries organised? Large-scale production requires logistics. Raw materials must be acquired, workshops must be supplied, skilled labour must be trained, and finished products must be distributed. Such systems resemble small industrial economies, yet almost no written records survive to explain how production was coordinated. The artifacts prove that manufacturing occurred, but the organisational methods behind that manufacturing have largely vanished. Thousands of inscriptions have been discovered throughout southern Arabia. Some provide valuable information about trade, politics, religion, and society. But many questions remain unanswered. Ancient cities depend on knowledge systems. Engineers require methods of teaching. Craftsmen require training. Builders require measurement standards. And administrators require record-keeping systems. The physical remains of Al-Okhdud demonstrate that such knowledge once existed. The problem is that very little of it survives. Perhaps the final mystery is why Al-Okhdud declined. The city occupied a strategic location, participated in regional trade, possessed manufacturing capabilities, and demonstrated significant engineering competence. Yet eventually it faded from prominence. Climate change, shifting trade routes, political instability, military conflict, and resource pressures have all been proposed as contributing factors. None fully explains the disappearance. Like many ancient cities, Al-Okhdud seems to have lost not only its population, but also much of its accumulated technical knowledge. The workshops fell silent, the furnaces cooled, and the engineers vanished. Only the ruins remained. What do you think? Were the craftsmen of Al-Okhdud simply masters of knowledge accumulated over generations? Or did they possess technological skills far more advanced than historians currently recognise? Share your thoughts in the comments below. Off the northern coast of Kenya, hidden among the islands of the Lamu archipelago, lie the ruins of Manda Island, an abandoned city that once stood at the centre of one of the most sophisticated maritime civilizations in Africa. For nearly 1,000 years, its builders quarried coral from the sea, manufactured durable lime mortar, engineered freshwater systems on a saltwater island and connected East Africa to trade networks stretching thousands of kilometers across the Indian Ocean. Yet many of the technologies that made this possible remain only partially understood today. The ruins of Manda became known through surveys and archaeological investigations conducted during the 20th century. Excavations revealed stone houses, mosques, wells, imported ceramics, coins, and evidence of extensive trade dating primarily between the 9th and 15th centuries. What initially appeared to be another Swahili settlement soon emerged as one of the oldest and most technologically intriguing urban centres on the East African coast. One of the first mysteries of Manda is its construction material. Unlike many ancient cities built from granite, sandstone, or limestone, Manda was largely constructed from coral stone. The builders extracted fossilized coral blocks from coastal reefs and transformed them into houses, mosques, courtyards, and defensive structures. At first glance, coral may seem like a weak material. In reality, it presents significant engineering challenges. Coral is porous, vulnerable to erosion, and difficult to shape consistently. Yet many walls at Manda survived centuries of tropical humidity, seasonal storms, salt exposure, and coastal winds. Archaeologists have identified structures with walls exceeding 0.5 meter in thickness, designed not only for stability but also for thermal regulation. The porous nature of coral helped reduce indoor temperatures in an environment where daytime temperatures often exceed 30 degrees Celsius. What remains uncertain is how builders achieved such consistency. Thousands of coral blocks had to be extracted, transported, shaped, and assembled with remarkable precision. No construction manuals survive, and no written instructions explain quarrying methods. The engineering knowledge appears to have vanished with the civilization itself. The achievement becomes even more impressive when compared to contemporary settlements elsewhere in East Africa, many of which continue to rely primarily on timber, mud, and thatch construction. Manda represented a completely different level of architectural sophistication. Perhaps the greatest technological mystery of Manda Island is not the stone itself, but the material that holds the stone together. Throughout the ruins, archaeologists have discovered mortar made from coral lime. This material was essential for constructing durable buildings, capable of surviving in one of the most aggressive environments imaginable. Producing lime is far from simple. To create lime mortar, coral must first be heated to temperatures approaching 800 to 1000 degrees Celsius. This process drives carbon dioxide from calcium carbonate and produces quicklime. The quicklime is then mixed with water to create hydrated lime before being transformed into mortar. The challenge is enormous. Maintaining temperatures near 1000 degrees Celsius requires precise control of fuel, airflow, furnace design, and burn duration. Modern lime production relies on carefully engineered kilns. The people of Manda achieved similar results using technologies that remain poorly documented. Even more mysterious is the durability of the final product. Many coral lime structures on the Swahili coast have survived for centuries despite constant exposure to salt-laden air. Engineers know that marine environments are among the most destructive settings for masonry. Salt crystals penetrate pores, expand, and gradually break materials apart. Yet some sections of ancient Swahili mortar continue to perform remarkably well. Researchers studying traditional Swahili construction have discovered that lime production often involved prolonged curing periods. Historical accounts suggest that lime paste could be stored and aged for months before use. Some mixtures may have included organic additives such as mangrove extracts, plant fibers, coconut products, or other local materials. The exact recipes remain uncertain. This creates an intriguing parallel with Roman concrete. Modern scientists continue to investigate why certain Roman harbour structures have survived for nearly 2,000 years. In a similar way, Manda's coral lime mortar may contain material properties and production techniques that are not fully understood. Experimental reconstructions have demonstrated that even small variations in burning temperature, coral source, or curing time can dramatically alter mortar performance. Yet, ancient builders repeatedly achieved successful results without modern measuring instruments. How did they determine optimal firing conditions? How did they evaluate material quality? How did they develop formulas capable of resisting centuries of coastal weathering? The ruins offer evidence of success, but the process itself remains largely hidden. Manda Island presents another engineering puzzle. The settlement flourished on a coastal island surrounded by salt water. Maintaining a large population under such conditions requires reliable freshwater supplies. Archaeologists have identified numerous wells, cisterns, and water management features throughout the site. Some wells were carefully positioned to access freshwater lenses floating above denser seawater beneath the island. Today, hydrogeologists understand this phenomenon scientifically. Fresh water, being less dense than salt water, can form a floating lens within porous island sediments. However, exploiting such a resource without contamination requires considerable practical knowledge. If wells are dug too deep, saltwater intrusion occurs. If extraction exceeds recharge rates, the freshwater lens collapses. If construction is poor, contamination becomes unavoidable. Yet Manda supported urban life for centuries. The builders apparently understood local hydrogeology well enough to maintain sustainable water access long before modern groundwater science existed. Excavations have uncovered imported ceramics from China, Persian pottery, glass beads from the Middle East, and coins originating far beyond East Africa. These artifacts reveal participation in one of the world's largest trade systems. During the medieval period, the Indian Ocean functioned much like the Silk Road. Seasonal monsoon winds allowed ships to travel between East Africa, Arabia, Persia, India, and Southeast Asia. The scale of navigation involved is astonishing. A voyage from the Swahili coast to western India could exceed 3,000 kilometers. Successful travel required understanding seasonal wind reversals, ocean currents, weather patterns, and celestial navigation. Unlike European sailors centuries later, Swahili navigators left few written technical descriptions. As a result, historians still debate how navigation knowledge was transmitted and maintained. Was it preserved through oral traditions, apprenticeships, specialized maritime guilds? The evidence demonstrates extraordinary capability, but the underlying system remains largely invisible. Manda was not a random collection of buildings. Archaeological surveys reveal organized neighborhoods, religious structures, public spaces, and transportation corridors arranged according to practical urban principles. Mosques occupied important positions, residential compounds were carefully planned, water access points were integrated into the settlement, and trade activities were linked to the harbour. Such organization implies coordinated planning rather than spontaneous growth. Yet no administrative records survive to explain who designed the city or how decisions were made. The urban layout suggests sophisticated governance, but the mechanisms behind that governance remain uncertain. Long before modern architects discussed sustainable design, the builders of Manda were already solving environmental challenges through engineering. Coral walls provided thermal mass, narrow streets generated shade, courtyards enhanced ventilation, and building orientation captured prevailing winds. Together, these features reduced indoor temperatures without mechanical cooling. Modern studies of traditional Swahili architecture have shown that passive cooling strategies can significantly improve thermal comfort in tropical climates. In some respects, the environmental design principles visible at Manda resemble concepts promoted by sustainable architects today. The difference is that Manda's builders developed these solutions centuries before air conditioning, computer simulations, or modern climate science. Dadan and Jabal Ikma lie in the Alula oasis of northwestern Saudi Arabia. Archaeologists began systematically studying the region during the 20th century, uncovering the remains of the ancient kingdoms of Dadan and Liyan, which flourished between roughly the 9th century BCE and the 1st century BCE. What initially appeared to be another desert archaeological site soon revealed something far more intriguing: evidence of advanced engineering, water management, large-scale stoneworking, and a surprisingly sophisticated knowledge system operating in one of the harshest environments on Earth. Today, Dadan and Jabal Ikma raise a question that archaeologists still cannot fully answer. How did an ancient civilization thrive for centuries in a landscape where survival itself should have been extraordinarily difficult? The greatest mystery begins with water. Modern Alula receives relatively little rainfall and experiences extreme seasonal temperature fluctuations. Yet archaeological surveys indicate that Dadan supported a substantial population for hundreds of years. Such a settlement could not exist without a reliable water supply. Excavations have uncovered wells, irrigation channels, reservoirs, and evidence of extensive agricultural activity, and some researchers estimate that thousands of people may have depended on these systems simultaneously. The challenge is understanding how they were designed. Water systems require precise gradients. A channel that slopes too steeply erodes, while a channel that is too flat stagnates. Modern engineers solve this problem using surveying equipment, laser measurements, and topographic modelling. The builders of Dadan possessed none of these tools, yet the surviving evidence suggests that they successfully distributed water across an oasis environment for generations. The comparison is striking. Similar hydraulic expertise appears at the ancient city of Petra in Jordan, where Nabatean engineers controlled flash floods and stored millions of litres of water. At Dadan, however, the technical documentation is completely absent. The infrastructure survives, but the methods behind it have vanished. Perhaps even more remarkable is the placement of ancient wells. Modern hydrogeologists use satellite imagery, geophysical surveys, and groundwater models to identify promising drilling locations. But ancient engineers had none of these advantages. Yet many of Dadan's wells appear to have been positioned with extraordinary effectiveness. The surrounding region contains complex sandstone formations capable of storing groundwater deep beneath the surface, and identifying productive locations would have required an intimate understanding of geology, terrain, seasonal runoff patterns, and subsurface water movement. How did they acquire that knowledge? Some scholars suggest centuries of accumulated observation, while others argue that ancient communities may have developed practical geological methods far more sophisticated than historians traditionally assumed. The truth remains uncertain. What is clear is that the success rate of their water infrastructure appears difficult to explain through simple trial and error alone. A short distance from Dadan stands Jabal Ikma, often described as one of the largest open-air libraries in the Arabian Peninsula. Hundreds of inscriptions cover the sandstone cliffs. At first glance, they appear to be historical texts, religious statements, territorial markers, and records of social life. Yet the real mystery lies in their execution. Many inscriptions display remarkable consistency in character size, spacing, and depth. This level of standardization is surprising. Ancient stone inscriptions elsewhere often vary dramatically depending on the skill of individual craftsmen. At Jabal Ikma, however, a significant number appear to follow consistent visual conventions. Did scribes use measurement grids? Did they employ marking systems that disappeared long ago? Did specialized schools train stone carvers according to standardized techniques? Archaeologists have no definitive answers. The inscriptions preserve the results of a system, but not the system itself. Among the most impressive structures at Dadan are tombs carved directly into towering sandstone cliffs. Several are positioned high above ground level, and even today, reaching some of these locations requires significant effort. The engineering challenge is obvious. How are workers transported to such heights? Where are the remains of scaffolding systems? How are symmetrical facades planned and executed on uneven rock surfaces? Researchers often compare these tombs with the rock-cut architecture of Petra. In both locations, builders carved monumental structures directly into cliffs, and the common theory suggests that work began from the top and progressed downward. Yet this explanation creates new questions. Constructing large-scale facades requires planning, measurement, and quality control, and a single major error could ruin months of labor. The precision visible at Dadan suggests that builders possessed reliable methods for transferring architectural designs onto vertical rock surfaces. Those methods remain largely unknown. One of the least appreciated mysteries concerns agriculture. Ancient inscriptions and archaeological evidence indicate that the oasis supported extensive farming activities. Crops likely included dates and other cultivated plants capable of surviving arid conditions. Agriculture in desert environments is fundamentally an engineering problem. Farmers must manage soil salinity, control water distribution, minimize evaporation, and maintain long-term fertility. Even small mistakes can render fields unusable. Yet Dadan remained occupied for centuries. This suggests that its inhabitants possessed a practical understanding of environmental management comparable to other ancient agricultural centers. Mesopotamia relied on the Tigris and Euphrates. Egypt depended on the Nile. Dadan had only a desert oasis. Its long-term success may therefore represent one of the most overlooked agricultural achievements of the ancient world. Dadan occupied a strategic position along the incense route, one of the most important commercial networks of antiquity. Frankincense, myrrh, spices, textiles, and luxury goods moved across thousands of kilometers of desert. Maintaining such trade required extraordinary logistical expertise. Caravans needed navigation systems, predictable water sources, route planning, resource management, and security. Modern transportation networks rely on maps, satellites, weather forecasting, and digital communication, while ancient traders relied on knowledge passed from generation to generation. The scale of the network is difficult to overstate. Some trade routes connected southern Arabia to the Mediterranean world, linking cultures separated by thousands of kilometers. The organizational knowledge required to maintain these routes may have been every bit as sophisticated as the engineering visible in stone. Perhaps the greatest mystery of Dadan and Jabal Ikma is not what survives, it is what disappeared. The people who lived here understood hydrology, geology, surveying, agriculture, logistics, architecture, and stoneworking. Their achievements required centuries of accumulated expertise. Yet almost none of their technical explanations remain. No engineering manuals describe the irrigation systems. No architectural plans explain the cliff tombs. No surveying documents reveal how construction sites were measured. No instructional texts describe how inscriptions were standardized across generations. Few abandoned buildings in Britain inspire more mystery than Denbigh's insane asylum. Long before modern hospitals relied on computers, sensors, air conditioning systems, and automated infrastructure, engineers in northern Wales created a self-contained institution capable of housing and supporting more than 1,500 patients and staff. Today, the massive ruins stand silent, their collapsing corridors attracting urban explorers and paranormal investigators. Yet the greatest mystery may not be the ghost stories, it may be the engineering. Located near the town of Denbigh in North Wales, the asylum opened in 1848 and eventually expanded into one of the largest psychiatric hospitals in Britain. Covering a vast area and operating almost like a small city, the institution required water systems, heating networks, ventilation infrastructure, food production, waste management, transportation logistics, and structural engineering on a scale rarely appreciated today. More than 175 years later, many aspects of how this enormous machine functioned remain surprisingly difficult to reconstruct. The ruins never disappeared. They remained visible throughout the 20th century after the hospital's closure in 1995. What changed was how researchers began to view the site. Initially, historians focused primarily on medical history. Archaeologists and preservation specialists later recognized something far more intriguing. Denbigh was not simply a hospital, it represented one of the largest surviving examples of Victorian institutional engineering. The main complex stretches across hundreds of meters of interconnected wards, administrative buildings, service corridors, utility systems, and support facilities. Historic records indicate that patient populations often exceeded 1,000 individuals. During peak periods, total occupancy, including staff, approached levels comparable to a small town. To understand the scale, consider this comparison. The average medieval castle housed only a few hundred permanent residents, and even many Roman forts contained fewer people than Denbigh supported on a daily basis. Yet Denbigh achieved this using 19th century technology. One of the least understood engineering achievements involves air circulation. Victorian doctors believed fresh air was essential for mental and physical health. Diseases such as tuberculosis were widespread, and poor ventilation was associated with illness. As a result, Denbigh's architects designed an elaborate airflow system throughout the structure. The corridors were unusually long, the ceilings exceptionally high, and the windows strategically positioned to maximize natural airflow. Internal shafts allowed warm air to rise through the building. Modern engineers recognize this as an application of the stack effect, in which warm air naturally moves upward, creating pressure differences that draw cooler air into lower levels. Today, skyscrapers use the same physical principle. What remains unclear is how effectively the system operated when the asylum housed over 1,000 people. Researchers examining surviving plans have discovered evidence of ventilation pathways hidden inside walls and roof spaces. However, many original records have been lost, making it difficult to reconstruct the complete network. Some experts believe Denbigh functioned as a giant passive climate control machine decades before modern environmental engineering became a formal discipline. Wales is not known for mild winters. Keeping thousands of rooms warm required enormous amounts of energy. Historical records indicate the institution operated large boiler systems that distributed heat throughout the complex. Steam and hot water networks extended beneath floors and through service tunnels. The challenge was not merely generating heat, it was distributing heat efficiently. Modern hospitals use computerized controls that continuously adjust temperatures, but Victorian engineers had no such technology. Yet they successfully maintained habitable conditions across a sprawling campus covering tens of thousands of square meters. Even today, engineers studying 19th century institutional buildings sometimes struggle to determine how temperatures were balanced between different wards. How are pressure levels regulated? How are heat losses minimized? How are failures prevented during severe winters? Many operational details disappeared when the hospital closed, taking practical knowledge with them. Beneath the visible structure lies another mystery. Like many large Victorian institutions, Denbigh contained an extensive network of service tunnels. These underground passages carried steam pipes, water lines, drainage systems, and maintenance routes. They allowed workers to move fuel and supplies while minimizing disruption above ground. Some sections remain inaccessible due to structural instability, while others have never been fully documented using modern survey techniques. This creates an unusual situation. Researchers can identify portions of the network, yet no one can state with complete confidence exactly how extensive the original system was. The tunnels raise a fascinating comparison with ancient engineering. Roman cities often concealed aqueducts and drainage channels beneath streets. Medieval castles incorporated hidden passages for defense and logistics. Denbigh appears to represent the Victorian version of the same concept, an invisible infrastructure network supporting a complex society above. Perhaps the most visible mystery is the survival of the building itself. Decades of abandonment have exposed the structure to rain, frost, vegetation, and vandalism. Roofs have collapsed, floors have deteriorated, yet substantial sections remain standing. Why? The answer appears to involve several engineering factors. Victorian bricks were often fired at high temperatures, producing exceptionally durable materials. Load-bearing walls distributed weight across massive structural elements. Arches redirected forces efficiently. Mortars were formulated for long-term performance. Some surviving walls continue to demonstrate remarkable stability despite losing portions of their supporting structures. Engineers studying historic buildings frequently encounter this paradox. Many 19th century structures exhibit lifespans that exceed modern expectations. The exact combination of craftsmanship, material quality, and construction methods responsible for this durability remains debated. Every city depends on water, and Denbigh was no exception. Supplying water for over 1,000 residents required careful planning. Drinking water, cooking, cleaning, sanitation, laundry services, and heating systems all depended on reliable distribution. Historical evidence suggests the institution maintained sophisticated water storage and drainage infrastructure. The challenge becomes clearer when viewed quantitatively. A modern hospital patient typically requires hundreds of litres of water per day when all operational needs are considered. Even conservative estimates suggest Denbigh may have processed hundreds of thousands of litres daily during peak operation. Without digital monitoring systems, maintaining such a network required remarkable technical competence. Much of the original infrastructure now lies buried, damaged, or inaccessible, leaving important questions unanswered. Perhaps the most unusual technological mystery involves the building's design philosophy. Victorian architects believed architecture itself could influence mental health. Natural light, open views, gardens, fresh air, and orderly environments were integrated into treatment strategies. Denbigh was carefully positioned to take advantage of surrounding landscapes. Large windows admitted sunlight, recreational grounds provided outdoor access, and internal layouts promoted supervision while preserving visual openness. Modern neuroscience increasingly recognizes that environmental design affects stress levels, recovery rates, and psychological well-being. This raises an intriguing possibility. Were 19th century designers intuitively applying principles that modern science is only now beginning to quantify? Few ancient ruins create as many unanswered questions as Segesta. Standing alone on a windswept hill in western Sicily, the city's most famous monument appears almost impossible. It is one of the best preserved Greek-style temples in the world. Its columns still stand after more than 2,400 years, and its geometry remains remarkably precise. Yet according to archaeological evidence, the temple may never have been finished. How can an unfinished building survive longer than many completed monuments? Even more puzzling, who built it? How did they build it? And why did they suddenly stop? Modern archaeology has uncovered part of the story, but the rest remains one of the most fascinating engineering mysteries of the ancient Mediterranean. Segesta is located in northwestern Sicily, approximately 65 kilometers west of Palermo, on the slopes of Mount Barbaro. The ruins occupy a strategic position overlooking valleys that connect the interior of Sicily with the Tyrrhenian Sea. Although the site was known throughout antiquity, systematic archaeological investigations began during the 18th and 19th centuries. Extensive excavations throughout the 20th century revealed a large urban centre containing fortifications, roads, sanctuaries, residential districts, a theatre, and the famous Doric Temple. The city was traditionally associated with the Elymians, a mysterious ancient people whose origins remain uncertain. Ancient Greek historians suggested they descended from survivors of Troy following the Trojan War, while modern archaeology offers alternative explanations, including local Sicilian origins mixed with influences from Greek and indigenous populations. Whatever their origin, the builders of Segesta possessed engineering capabilities far beyond what many historians once assumed. The most famous structure at Segesta immediately presents a paradox. Constructed around 430–420 BCE, the temple measures approximately 61 meters long and 26 meters wide. 36 massive Doric columns surround the structure, and each column stands nearly 10 meters high and weighs many tons. At first glance, the building appears complete. However, a closer inspection reveals something astonishing. Many columns still retain protruding lifting bosses that ancient builders normally removed after construction. The fluting typically carved into Doric columns was never finished. No evidence exists for a completed roof, and archaeologists have found no clear remains of an internal sanctuary chamber, known as the cella, which would normally house the deity. In other words, the temple looks complete from a distance but unfinished when examined closely. This contradiction has puzzled researchers for generations. Ancient construction projects occasionally stopped because of war, political instability, or economic collapse. However, Segesta's temple appears to have reached an unusually advanced stage before work ceased. Thousands of tons of stone had already been quarried, transported, shaped, elevated, and assembled. Why invest enormous resources only to abandon the project near completion? No surviving text provides an answer. The temple's location creates another mystery. The structure stands on a sloping ridge surrounded by uneven terrain. Modern engineers would begin such a project with extensive surveying equipment, topographic measurements, and structural calculations. Ancient builders possessed none of these technologies. Yet surveys reveal remarkable geometric precision. The columns align with extraordinary accuracy. The platform remains stable despite centuries of weathering and seismic activity, and load distribution across the structure appears carefully balanced. The challenge becomes even more remarkable when considering the available tools. Ancient surveyors likely relied on ropes, plumb bobs, measuring rods, and simple sighting instruments. Despite these limitations, they achieved results comparable to those seen in some of the finest Greek temples. The Parthenon in Athens demonstrates famous geometric refinements such as column entasis and subtle curvature corrections. Segesta displays similar levels of precision despite being constructed by a population that was not fully Greek. This raises a difficult question. How did the Elymians acquire such sophisticated surveying knowledge? One of the greatest mysteries involves logistics. The temple required thousands of stone blocks extracted from nearby quarries. Individual blocks weighed several tons, and some column drums likely exceeded 10 tons. Today, cranes, trucks, and hydraulic lifting systems make such operations routine. Ancient builders had none of these advantages. Experimental archaeology has demonstrated that moving multi-ton stones using ropes, rollers, Sledges and manpower is possible. The problem is scale. A structure the size of Segesta required thousands of successful operations conducted with extraordinary coordination. Every stone had to arrive in the correct sequence. Every column drum had to be lifted and aligned, and every block had to fit within tight tolerances. Researchers studying large ancient construction projects often compare them to military campaigns, because both require planning, resource management, labour organisation, food distribution, transportation networks, and technical expertise. The Temple of Segesta suggests a level of organisational sophistication rarely associated with small ancient populations, yet almost no records survive to explain how this logistical system operated. Sicily occupies one of the most geologically active regions of the Mediterranean. The island sits near the boundary between the African and Eurasian tectonic plates. Throughout recorded history, earthquakes have repeatedly damaged cities across Sicily. Many ancient structures collapsed long ago, yet Segesta's temple remains standing. The survival of the building is not simply a matter of luck. Structural engineers studying ancient architecture have repeatedly found that many classical builders intuitively understood principles that modern science would later formalize mathematically. Massive stone blocks distribute forces efficiently, column spacing influences load transfer, and foundation design affects stability during seismic events. Segesta appears to incorporate many of these advantages. The mystery is whether the builders understood these principles theoretically or arrived at them through centuries of practical experimentation. Either explanation implies a highly advanced engineering tradition. Several hundred meters above the temple lies another remarkable structure. The Theatre of Segesta sits near the summit of Mount Barbaro at an elevation exceeding 400 meters. The location offers breathtaking views across western Sicily toward the sea. More importantly, it demonstrates extraordinary environmental planning. Ancient theatres were not simply places for entertainment. Their builders had to understand terrain, visibility, crowd movement, drainage, and acoustics. Modern acoustic studies show that many Greek and Roman theatres amplify speech naturally through geometric design. Carefully calculated seating arrangements help project sound toward large audiences without electronic amplification. Segesta's theatre appears to achieve these effects while simultaneously adapting to a challenging mountain environment. How ancient builders optimized these factors without modern acoustic science remains only partially understood. Perhaps the most overlooked mystery involves the transmission of knowledge itself. Segesta existed within a highly competitive Mediterranean world that included Greeks, Phoenicians, Carthaginians, and indigenous Sicilian cultures. The city's architecture reveals influences from multiple civilizations. Its temple follows Greek Doric conventions, its political alliances shifted between rival powers, and its urban planning reflects both local and external traditions. This mixture raises an intriguing possibility. Rather than developing in isolation, Segesta may have participated in a vast ancient knowledge network connecting engineers, architects, craftsmen, surveyors, and builders across the Mediterranean. If true, technological ideas may have travelled much farther and faster than historians once believed. Unfortunately, the written documentation needed to prove this theory has largely disappeared. What do you think? Why was the Temple of Segesta abandoned, and how much of its builders' knowledge has been lost forever? Let us know your thoughts in the comments below. In the heart of Rome, Italy, stands the Colosseum, a monument built on land that was once occupied by the artificial lake of Emperor Nero's Domus Aurea. Today it is recognized as the largest amphitheatre ever built by the Roman Empire. Yet beneath its iconic arches lies a mystery far greater than gladiatorial combat. Nearly 2,000 years after its construction, engineers continue to study the structure because many aspects of its design appear astonishingly advanced even by modern standards. Construction began around 72 CE under Emperor Vespasian and was largely completed by 80 CE under his son Titus. Archaeological evidence indicates that the project consumed approximately 100,000 cubic meters of travertine stone, thousands of tons of iron clamps, millions of Roman bricks, and vast quantities of concrete. Despite this enormous scale, the building was completed in less than a decade. To understand how remarkable this achievement was, consider a modern sports stadium. Contemporary arenas often require advanced machinery, computer modelling, steel cranes, and years of planning. Yet Roman engineers achieved something comparable using manual labour, animal power, and tools that would appear primitive today. The speed alone remains one of the first great mysteries of the Colosseum. The structure measures approximately 189 metres long, 156 metres wide, and nearly 48 metres high. More impressive is the precision of its geometry. The elliptical design appears remarkably accurate across the entire footprint. Modern surveyors can create such layouts using laser equipment and digital calculations. Roman builders relied on ropes, measuring rods, and geometric principles. Exactly how they maintained such precision over an area exceeding 24,000 square meters remains uncertain. Many researchers compare the challenge to laying out a giant mathematical figure on the ground without modern instruments. Even small errors at the beginning would multiply dramatically across the finished structure. Yet the Colosseum exhibits a level of consistency that continues to impress engineers today. The second mystery emerges from the building's incredible durability. Rome lies within a region affected by seismic activity. Throughout its history, the Colosseum has experienced earthquakes, weathering, floods, lightning strikes, stone theft, pollution, and nearly 2 millennia of natural deterioration. A major earthquake in 1349 destroyed part of the southern outer wall, yet much of the structure remains standing. Modern structural studies suggest that the secret may lie in the building's ring-shaped design. Hundreds of arches distribute loads through interconnected pathways rather than concentrating stress in a few locations. The structure behaves less like a rigid block and more like a flexible network capable of absorbing movement. Some engineers have compared this principle to modern earthquake-resistant architecture. The comparison is remarkable because Roman builders possessed no formal understanding of seismic engineering in the modern scientific sense. Were they simply fortunate, or had centuries of practical experimentation produced knowledge that functioned like earthquake engineering long before the field officially existed? Perhaps the most mysterious feature was invisible to spectators. Beneath the arena floor existed a vast underground complex known as the Hypogeum. Excavations reveal corridors, chambers, cages, storage rooms, and mechanical systems extending beneath the entire structure. What archaeologists discovered shocked many historians. The underground network contained dozens of elevators and lifting platforms capable of raising animals, scenery, and performers directly into the arena above. Lions, leopards, bears, and even larger animals could appear seemingly from nowhere. Entire stage sets could emerge through hidden trapdoors. Researchers estimate that at least 28 major elevators operated simultaneously. Some reconstructions suggest there may have been even more. The engineering challenge is staggering. These machines relied entirely on human muscle power. Teams of workers pulled ropes connected to capstans and pulleys. Yet the system had to function reliably before audiences that sometimes exceeded 50,000 spectators. No complete engineering blueprint survives. Modern reconstructions are based entirely on archaeological remains. As a result, significant questions remain unanswered regarding synchronization, load limits, operating procedures, and maintenance methods. The Colosseum was not merely a stadium, it was arguably the largest mechanical theatre ever constructed in the ancient world. Another puzzle involves one of the largest retractable roof systems ever attempted before modern times. Ancient sources describe a massive awning known as the velarium. Supported by hundreds of ropes and towering masts around the perimeter, the canopy could shade large sections of the audience from the Mediterranean sun. Researchers believe Roman sailors from the imperial fleet were responsible for operating the system because of their expertise with rigging and sail management. The problem is that almost none of the actual mechanism survives. Archaeologists have identified sockets for masts around the upper perimeter. Ancient texts mention the canopy. Artistic depictions provide clues. Yet no complete description explains exactly how the system functioned. Even modern engineers debate how such a massive fabric structure could remain stable during changing wind conditions. Some reconstructions suggest that operating the velarium may have required hundreds of personnel working in coordination. If accurate, the Colosseum possessed a movable roofing system more sophisticated than many large structures built over 1,000 years later. One of the most controversial mysteries concerns water. Several ancient writers claimed that early events included mock naval battles known as naumachiae. According to these accounts, the arena could be flooded and used for staged combat between ships. The concept seems almost impossible. The arena occupied approximately 6,000 square meters. Filling such an area with sufficient water for naval demonstrations would require immense hydraulic capacity. Water would then need to be drained rapidly to prepare for later events. Some scholars believe the earliest version of the arena floor may have allowed temporary flooding before the hypogeum was constructed. Others argue that ancient accounts exaggerated what actually occurred. The debate remains unresolved. If large-scale flooding truly occurred, Roman engineers possessed hydraulic capabilities that remain difficult to fully reconstruct. The materials themselves introduce another mystery. The Colosseum relied heavily on Roman concrete, one of the most studied ancient construction materials in the world. Modern laboratory analysis has revealed surprising properties. Unlike many contemporary concretes that gradually weaken, certain Roman formulations appear to strengthen over time through chemical reactions involving lime and volcanic ash. Recent research has identified microscopic mineral formations that may help seal small cracks naturally. Some scientists describe this phenomenon as a form of self-healing concrete. This discovery has raised an uncomfortable question. If modern materials science is still learning from Roman concrete after 2,000 years, how much did Roman builders actually understand about the material they were creating? Were they following recipes developed through generations of experimentation, or did they possess a deeper understanding of material behavior than historians currently recognize? The logistics behind the Colosseum create yet another puzzle. The construction required enormous quantities of stone transported from quarries at Tivoli, approximately 30 kilometers away. Estimates suggest tens of thousands of wagon journeys may have been necessary. Massive blocks weighing several tons each had to be cut, transported, lifted, positioned, and secured with extraordinary precision. Without modern cranes, engines, hydraulic systems, or powered transportation, the project demanded organizational capabilities on a scale comparable to major state infrastructure projects today. Historians often focus on the building itself, yet the management system required to coordinate thousands of workers, craftsmen, engineers, suppliers, and transport crews may represent an equally impressive achievement. In Rajasthan, India, near the city of Udaipur, More than 250 stone cenotaphs stand beneath the scorching desert sun. Built across centuries by the rulers of Mewar, these monuments appear peaceful and familiar. Yet behind their elegant domes lies a technological mystery that archaeologists and engineers still struggle to fully explain. How did pre-industrial builders construct hundreds of precisely balanced stone structures that continue to survive after centuries of heat, monsoon rains, and natural weathering? The Royal Cenotaph Complex at Ahar became known through historical records of the Mewar dynasty and later archaeological surveys. While historians initially viewed the site primarily as a royal cremation ground, closer examination revealed something far more intriguing: a vast collection of stone structures displaying remarkable consistency in design, geometry, and engineering despite being constructed over several hundred years. The greatest technological puzzle of Ahar begins with its domes. At first glance, the domes appear simple. They are not as massive as the Pantheon in Rome, nor as famous as the Dome of Hagia Sophia. Yet what makes them extraordinary is the sheer number of them. More than 250 cenotaphs occupy the site, many featuring carefully proportioned domes supported by columns and elevated platforms. Modern structural engineers understand that domes are among the most efficient architectural forms ever created. A properly designed dome redirects gravitational forces into compression, allowing stone to support tremendous weight. However, this efficiency only works when geometry is extremely precise. Even small construction errors can create uneven stress distribution, and over decades or centuries those stresses can produce cracks, distortions, and eventual collapse. Yet many of Ahar's domes remain standing after hundreds of years. This raises an obvious question. How did the builders achieve such consistency without modern mathematics, structural software, laser measurements, or steel reinforcement? Researchers studying historical architecture often point out that ancient builders relied on accumulated practical knowledge rather than formal engineering calculations. But practical knowledge alone does not fully explain the remarkable uniformity seen throughout the complex. Many domes display proportional relationships that appear carefully standardized. Column spacing, roof curvature, and load distribution often follow recurring patterns. This suggests that builders possessed highly refined construction rules, even if those rules were never written down. The mystery becomes even more fascinating when one considers the environmental conditions. Rajasthan experiences extreme temperature fluctuations. Summer temperatures can exceed 45 degrees Celsius. During monsoon seasons, heavy rainfall introduces moisture into foundations and stone surfaces. Thermal expansion and contraction repeatedly stress masonry structures year after year. For comparison, many modern concrete structures require significant maintenance after only 50 to 100 years. Yet numerous cenotaphs at Ahar have survived several centuries. The builders clearly understood something about structural stability that allowed these monuments to endure far beyond what might be expected. The problem is that their methods largely disappeared. No engineering manuals survive. No architectural blueprints have been discovered. The structures remain, but the knowledge behind them has largely vanished. The domes are only part of the mystery. Many cenotaphs contain intricately carved columns, decorative arches, and finely shaped stone elements. These features required extraordinary craftsmanship. Stone carving may seem straightforward, but working with marble and sandstone presents significant challenges. Every block contains natural weaknesses, and internal fractures can remain invisible until a tool strike suddenly splits an entire section. Modern stone-cutting operations use diamond blades, computer-guided equipment, and precision measuring systems. The craftsmen of Ahar relied on hand tools, iron chisels, and accumulated experience. Yet the results often display remarkable symmetry. Archaeologists studying traditional stoneworking techniques have repeatedly found that ancient craftsmen achieved levels of precision that appear surprisingly sophisticated. Small deviations in carving can multiply across a structure, eventually producing visible distortions. The builders of Ahar somehow avoided many of these problems, and how they maintained such accuracy across hundreds of monuments remains poorly understood. One of the least visible mysteries lies underground. Every surviving structure depends upon its foundation. Without proper foundations, even perfectly designed buildings eventually fail. Ahar's builders faced difficult environmental conditions. Soil properties change as moisture levels fluctuate throughout the year. During monsoon periods, water infiltration can weaken supporting ground, while during dry seasons, soil contraction can create new stresses. Modern geotechnical engineers spend months analyzing soil before constructing major projects. The builders of Ahar had no drilling rigs, no computer models, and no laboratory testing equipment. Yet many structures remain remarkably stable. This suggests a sophisticated understanding of local geology and drainage conditions. Builders likely recognized which areas could safely support heavy stone loads and which could not. Unfortunately, almost none of that knowledge survives in written form. Another mystery involves time itself. Unlike many famous monuments, Ahar was not built during a single construction campaign. The complex expanded gradually as generations of Muva rulers added new cenotaphs. This should have produced architectural chaos. Different builders working across different centuries often create inconsistent styles, changing dimensions and conflicting layouts. Yet Ahar displays a surprising degree of visual coherence. Many structures appear connected by shared design principles, architectural proportions remain relatively consistent, and spatial organization follows recognizable patterns. This raises an intriguing possibility. Did the builders possess a long-term planning tradition passed from one generation to the next? Perhaps master builders maintained design rules that survived for centuries through oral transmission. If so, that knowledge system has almost completely disappeared. The monument survived, but the planning system did not. Building hundreds of stone monuments required more than architectural knowledge. It required tools. Every carved column, every decorative arch, and every shaped stone block depended upon metal implements capable of withstanding enormous stress. Producing high-quality iron tools was itself a technological challenge. Ancient metallurgists needed to control furnace temperatures approaching 1,200 degrees Celsius. They had to manage airflow, fuel quality, ore composition, and carbon content. Even small variations could dramatically affect tool performance. India possesses one of the world's oldest metallurgical traditions. Ancient Indian steel, particularly wootz steel, became famous across Asia and the Middle East for its exceptional quality. Although direct evidence connecting Ahar's builders to specific metallurgical innovations remains limited, the scale of construction strongly suggests access to highly effective metalworking technology. The question is how advanced that technology truly was. Perhaps the most overlooked mystery is the location itself. Ahar is not merely a medieval royal cemetery. The region is also associated with the ancient Ahar Banas culture, which flourished roughly 4,000 years ago. Excavations have uncovered evidence of early settlements, copper metallurgy, ceramics, and organized habitation. This creates a fascinating historical overlap. Thousands of years before the royal cenotaphs appeared, people were already developing technological traditions in the same region. Was the location chosen purely by coincidence, or did later rulers deliberately associate themselves with a landscape that had been culturally significant for millennia? The answer remains uncertain. Were the builders of Ahar simply master craftsmen, Or did they possess engineering knowledge far more sophisticated than history has yet recognized? Maski, southern India. More than 2,200 years ago, someone stood before a massive rock and carved a message that would survive longer than entire kingdoms. The inscription appears simple, yet behind its weathered letters lies evidence of surveying, metallurgy, logistics, administration, and engineering knowledge that historians still struggle to fully explain. The inscription was discovered near the town of Maski in present-day Karnataka. What made the discovery extraordinary was a single detail. Unlike many other imperial inscriptions, this edict explicitly mentioned the name Ashoka, helping scholars confirm that the mysterious ruler known elsewhere as Devanampriya was in fact Emperor Ashoka of the Mauryan Empire. But while historians celebrated the historical identification, another question quietly emerged. How was such a vast communication system physically created more than 2 millennia ago? The Maski Rock Edict is only one of dozens of inscriptions attributed to Ashoka, and these inscriptions are scattered across an enormous territory stretching from Afghanistan to southern India. The Mauryan Empire at its height covered roughly 5 million square kilometers, making it one of the largest political entities of the ancient world. For comparison, the Roman Empire at its peak covered approximately 5 million square kilometers. The Achaemenid Persian Empire controlled around 5.5 million square kilometers, and Alexander's empire reached about 5.2 million square kilometers before fragmenting. What makes Ashoka's inscriptions remarkable is not merely their existence, but their consistency. Messages separated by hundreds or even thousands of kilometers often contain nearly identical moral directives, administrative instructions, and political ideas. Today, governments rely on satellites, telecommunications networks, digital databases, and printing systems to maintain consistency across large territories. The Mauryan administration possessed none of these technologies, yet somehow officials managed to distribute standardized texts across one of the largest empires of the ancient world. Archaeologists continue to debate how such a communication network functioned. Did official scribes travel continuously between provinces? Were master copies maintained in administrative centers? Did relay systems similar to Persian courier networks operate throughout the empire? No complete administrative manuals have survived to answer these questions. The inscriptions remain, but the system that produced them has vanished. At first glance, the letters of the Maski inscription appear ordinary. Closer inspection reveals a more complicated picture. The inscription was carved onto an uneven natural rock surface rather than a carefully prepared monument, yet the characters maintain remarkably consistent proportions. Anyone who has attempted stone carving understands the challenge. Every strike of a hammer transfers force unpredictably through the rock, and small mistakes can fracture entire sections. Modern stonemasons often rely on steel templates, precision measuring tools, laser guides, and surface preparation techniques. Ancient craftsmen possessed none of these technologies. Nevertheless, the Brahmi characters display a surprising degree of standardization. The challenge becomes even greater when one considers the broader Ashokan inscription program, as similar writing styles appear across hundreds of locations throughout the empire. This suggests that scribes and stoneworkers may have followed standardized design rules. Yet no surviving instruction manuals explain how these standards were taught, measured, or enforced. The engineering process behind the inscriptions remains largely invisible. Why was Maski chosen? This question seems simple, but may reveal sophisticated planning. Ancient inscriptions were expensive projects, as labor, transportation, skilled craftsmen, and administrative oversight all required resources. As a result, location mattered. Many Ashokan inscriptions occupy strategic positions near trade routes, population centres, water sources or transportation corridors, and Maski appears to fit this pattern. This raises the possibility that Mauryan administrators conducted large-scale geographic assessments before selecting inscription sites. Modern planners rely on satellite imagery, topographic surveys, GIS software, and aerial photography. Ancient surveyors relied solely on human observation, yet they repeatedly selected locations that maximize visibility and accessibility. The achievement becomes even more impressive considering the size of the empire. Without modern maps, how did officials coordinate site selection across millions of square kilometers? The answer remains uncertain. More than 22 centuries have passed since the inscription was carved, and the letters are still visible. This durability is astonishing. Rock surfaces experience constant attack from environmental forces. Temperature fluctuations create expansion and contraction. Wind carries abrasive particles. Rainwater slowly dissolves minerals, and biological growth can penetrate microscopic cracks. Over centuries, these processes can erase entire inscriptions, yet substantial portions of the Maski inscription remain legible. Some researchers believe the choice of rock may not have been accidental. Ancient builders often demonstrated practical geological knowledge. Roman engineers selected volcanic materials that contributed to exceptionally durable concrete. Egyptian quarry workers carefully chose stone types for different monuments, and Inca builders identified rock formations resistant to earthquakes. Could Mauryan craftsmen have possessed similar expertise? The possibility cannot be ruled out. If so, the inscription represents not only writing but also applied geological engineering. The Maski inscription was written in the Brahmi script. Today, Brahmi is recognized as one of the most influential writing systems in history, and numerous South Asian and Southeast Asian scripts ultimately trace their origins to it. Yet Brahmi itself remains controversial. Scholars continue debating how it emerged, how quickly it spread, and how it became standardized. The existence of the Maski inscription implies much more than literacy. It suggests the presence of trained scribes, educational systems, administrative schools, copying procedures, and quality control mechanisms. To maintain consistency across an empire, information had to be transmitted accurately from one region to another. Even small copying errors can rapidly accumulate. Modern researchers studying manuscript traditions have shown that textual transmission often introduces significant variations over time. Yet many Ashokan inscriptions display striking consistency. This implies a level of bureaucratic organization that is difficult to reconstruct from surviving evidence alone. Of all the puzzles surrounding the Maski Rock Edict, perhaps none is more fascinating than the tools used to create it. Every visible letter is evidence of metallurgy. To carve deeply into stone, workers required chisels capable of withstanding thousands of repeated impacts. This sounds simple, but in reality it is an extremely demanding engineering challenge. Stone is unforgiving. Every hammer strike generates intense localized stress. Weak metal deforms rapidly, poorly forged tools fracture, and soft edges become blunt after only limited use. Ancient craftsmen therefore faced a difficult problem. They needed tools hard enough to cut stone yet tough enough to resist breaking. Achieving this balance requires sophisticated control of metallurgy. Archaeological evidence from the Mauryan period indicates widespread iron production. Excavations across ancient India have revealed furnaces, slag deposits, iron artifacts, and evidence of advanced metalworking traditions. Experimental archaeologists have demonstrated that producing effective carving tools requires temperatures approaching or exceeding 1,100 degrees Celsius during various stages of iron production and forging. Maintaining such temperatures without modern instrumentation is extraordinarily difficult. Airflow must be controlled carefully, fuel quality must remain consistent, furnace geometry affects combustion efficiency, and ore composition influences final metal properties. Even slight variations can dramatically alter performance. Modern blacksmiths use thermometers, controlled furnaces, and metallurgical analysis. Mauryan smiths possessed none of these advantages, yet their tools succeeded. The evidence is carved directly into stone. Some researchers compare this challenge to the mysteries surrounding Roman engineering. Roman builders created concrete capable of surviving marine environments for nearly 2,000 years, and modern scientists continue studying the material's unique chemistry. Similarly, the metalworkers behind Ashoka's inscriptions may have possessed practical knowledge that has largely disappeared. We know the results, but we do not fully understand the process. How were iron ores selected? How were furnace temperatures estimated? How were tool edges hardened? How frequently were chisels replaced? How were thousands of craftsmen trained to maintain consistent quality? Archaeology has only partial answers. The technology is visible, but the expertise remains largely hidden. In the heart of northern Spain, roughly 10 kilometers west of Vitoria-Gasteiz in the Basque Country, lie the ruins of Iruna-Valea, one of the largest Roman cities ever discovered in the region. Archaeologists have studied the site for decades, uncovering walls, houses, workshops, roads, and thousands of artifacts. Yet, despite years of excavation, Iruna-Valea remains surrounded by mysteries that extend far beyond its famous controversies. What makes this site remarkable is not simply what archaeologists have found. It is what the discoveries reveal about engineering, urban planning, material science, and technological knowledge that appears far more sophisticated than many would expect from a provincial Roman settlement. The city raises a fascinating question. How did a community on the edge of the Roman Empire develop infrastructure and construction technologies that continued functioning for centuries, while much of the knowledge behind them eventually disappeared? Iruna-Valea occupies a strategic plateau overlooking the Zadorra River in northern Spain. The location was ideal for controlling regional trade routes, connecting the Iberian interior with the northern coast. Archaeological investigations began in the 19th century, but large-scale excavations accelerated during the 20th and 21st centuries. Researchers eventually identified a settlement covering approximately 80 to 100 hectares, making it one of the most significant Roman urban centers in the Basque region. Excavations revealed an extensive network of roads, defensive walls, residential districts, industrial areas, and public buildings. Beneath the soil lay evidence of nearly 2,000 years of human activity. Yet the deeper archaeologists dug, the more questions emerged. The first mystery begins with the city's placement. Modern topographic studies show that the plateau provided natural defensive advantages, but constructing a large urban centre there required solving numerous engineering challenges. The terrain contained uneven elevations, drainage issues, and geological variations that could potentially destabilize major structures. Roman surveyors somehow transformed this landscape into a functioning city. Without satellites, aerial photography, GPS, or laser scanning, they established road grids, building alignments, and infrastructure systems that remained operational for centuries. Modern archaeologists, using digital terrain models, have discovered that many major structures appear carefully positioned to maximize natural drainage while minimizing erosion risk. This level of environmental adaptation resembles planning strategies seen at Roman cities such as Pompeii and Augusta Emerita, suggesting that sophisticated surveying knowledge extended even to distant provincial settlements. Exactly how surveyors achieved such accuracy using only ancient instruments remains a subject of ongoing research. No ancient city could survive without water. This fact creates one of the greatest mysteries at Valea. Archaeologists have identified drainage channels, water management features, and evidence of distribution systems. However, much of the original hydraulic network has disappeared. Estimating the city's population is difficult, but even a settlement of several thousand inhabitants would have required enormous amounts of water every day. Modern studies suggest that Roman urban residents could consume anywhere from 50 to more than 200 litres of water per person daily, depending on local infrastructure. That means the city may have needed hundreds of thousands of litres of water every day. Where exactly did all that water originate? How was it transported? What gradients were used? How were seasonal fluctuations managed? The surviving evidence demonstrates that a sophisticated hydraulic system once existed, yet much of its design remains hidden beneath later deposits or has been lost entirely. This mirrors similar mysteries surrounding Roman water systems throughout Europe, where the infrastructure survives only in fragments while the engineering calculations themselves have vanished. One of the most impressive discoveries at Valea is its defensive wall system. During the later Roman period, massive fortifications were constructed around the city. Some sections reached several meters in thickness and incorporated enormous quantities of stone and mortar. What makes these walls remarkable is their durability. For nearly 2,000 years, they have endured winter freezing cycles, heavy rainfall, temperature fluctuations, biological weathering, and ground movement. Modern engineers understand many aspects of Roman construction, but certain questions remain unresolved. Why do some Roman walls survive far longer than many medieval structures? What exact mortar compositions were used? How did builders optimize load distribution without modern structural calculations? Laboratory studies of Roman mortars elsewhere in the empire have revealed complex chemical interactions involving lime, volcanic materials, and mineral reactions that can strengthen structures over time. Whether similar mechanisms contributed to the longevity of Valea's walls remains an active area of investigation. Every excavation season produces evidence of remarkable craftsmanship. Researchers have recovered ceramics, glass vessels, metal tools, building materials, and decorative elements. Many artifacts remain in surprisingly good condition despite spending centuries underground. This raises important technological questions. Ancient craftsmen controlled firing temperatures without thermometers. They produced durable ceramics without computerized kilns. They manufactured glass with consistent properties despite lacking modern chemical analysis. They created pigments capable of surviving centuries of burial. Today, scientists use electron microscopes, X-ray diffraction, and spectroscopic analysis to study these materials. Yet understanding a material's composition is not the same as understanding the practical knowledge used to create it. The formulas survive, but the expertise largely does not. This pattern appears repeatedly throughout archaeology. Among the most impressive Roman innovations was the hypocaust system. Evidence from Roman settlements across the empire indicates that heated air could be circulated beneath floors and through wall cavities to warm buildings. At first glance, this sounds relatively simple. In reality, it required extraordinary engineering. Builders had to calculate airflow paths, control temperatures, prevent structural damage, and maintain efficient fuel consumption. Modern computational fluid dynamics simulations have demonstrated that some Roman heating systems achieved surprisingly effective thermal distribution. The mystery is not whether the technology worked. The mystery is how generations of engineers optimized these systems without modern physics, modern mathematics, or advanced instrumentation. The people responsible for these designs understood heat movement through direct observation and accumulated experience. much of that knowledge was never written down. Large cities require vast quantities of resources. Stone had to be quarried, timber had to be harvested, lime had to be produced, metals had to be transported, food had to support workers, everything had to arrive on schedule. Researchers studying Roman construction projects estimate that major urban developments could require tens of thousands of tons of material. At Iruna Valea, every wall, road, workshop, and public structure represents an enormous logistical achievement. Without trucks, cranes, railways, or engines, ancient builders coordinated supply networks across significant distances. Modern project managers rely on software to organize large construction operations. Roman administrators relied on experience, records, manpower, and organizational systems that remain only partially understood. The city itself proves their success. The methods behind that success remain largely invisible. What do you think? Were the builders of Iruna Valea simply applying standard Roman engineering? Or does the city preserve evidence of technological knowledge far more sophisticated than historians currently recognize? Share your thoughts in the comments below. Brahmagiri in Karnataka, southern India, appears at first to be little more than a hill surrounded by ancient stone circles. Yet beneath its soil lies evidence of engineering knowledge, iron production, and construction techniques that continue to raise questions more than 2,000 years later. The site gained international attention in 1947 when British archaeologist Mortimer Wheeler conducted systematic excavations and uncovered extensive megalithic burials, iron artifacts, pottery, and evidence of a sophisticated society that flourished during the Iron Age of southern India. What archaeologists found was not merely a cemetery, it was a technological landscape. Among Brahmagiri's most striking features are its megalithic stone circles. Hundreds of stones were carefully arranged to mark burial chambers hidden beneath the ground. At first glance, the structures appear simple, but closer examination reveals something more intriguing. Many circles display surprisingly consistent geometries. The stones were positioned to create nearly symmetrical layouts, despite being constructed long before modern surveying instruments existed. Some circles measure several meters across and contain underground chambers built from massive stone slabs. Creating such layouts required more than brute force. Builders needed methods for measuring distances, maintaining alignment, and preserving circular shapes across uneven terrain. Modern engineers accomplish similar tasks using measuring tapes, transit levels, and digital surveying equipment, yet the people of Brahmagiri possessed none of these tools. Even so, they achieved results that remained recognizable for over 2 millennia. The question remains unanswered. What surveying methods allowed these ancient builders to organize large numbers of stones with such consistency? The burial chambers beneath the circles were constructed using large granite slabs, some weighing hundreds of kilograms and occasionally exceeding a ton. Transporting stones of this size presents a significant engineering challenge even today. Experiments conducted on megalithic construction elsewhere in the world suggest that moving a single 1-ton block may require dozens of workers operating in perfect coordination, with friction, terrain, weather conditions, and stability all becoming critical factors. Brahmagiri sits within a landscape dominated by rocky hills and granite outcrops. Extracting suitable slabs, transporting them across uneven ground, and positioning them with precision would have required extensive planning. No written instructions survive, and no ancient diagrams explain the process. Like the builders of Stonehenge in Britain or the craters of the Moai statues on Easter Island, the people of Brahmagiri left behind the final product, but not the engineering manual. The burial chambers themselves represent another technological puzzle. Many consist of carefully fitted stone slabs arranged to create enclosed spaces capable of surviving thousands of years underground. These structures had to withstand soil pressure, seasonal moisture changes, and long-term geological stress. Modern archaeological studies indicate that some chambers remained remarkably intact despite centuries of environmental exposure. This durability suggests a practical understanding of structural stability. The builders knew which stones could support weight, how to position slabs to prevent collapse, and how to distribute loads without mortar or metal reinforcement. Yet none of this knowledge was recorded. The engineering principles survive only in stone. Perhaps the most important discoveries at Brahmagiri are the iron artifacts. Excavations revealed knives, spearheads, arrowheads, agricultural tools, and various iron objects dating to the early Iron Age. These finds demonstrate that the inhabitants possessed advanced metallurgical capabilities. Producing iron is far more difficult than producing copper. Copper melts at approximately 1085 degrees Celsius, while iron requires temperatures approaching 1200 degrees Celsius during bloomery production. Achieving such temperatures demands careful control of furnace design, airflow, fuel quality, and ore selection. Even slight mistakes can ruin an entire smelting operation. Experimental archaeologists attempting to recreate ancient iron production frequently encounter failures despite having access to modern scientific knowledge. Yet the metallurgists of Brahmagiri succeeded repeatedly, and their iron tools prove it. The mystery is not whether they understood metallurgy, the mystery is how they understood it so well. Of all Brahmagiri's mysteries, this may be the most fascinating. Ancient iron production was not a matter of simply heating rock until metal appeared. Every stage required precise, practical knowledge. The furnace needed the correct dimensions, the charcoal required specific burning properties, the ore needed suitable chemical composition, and the airflow had to remain within an effective range. Modern metallurgical analysis demonstrates that bloomery furnaces operate within surprisingly narrow performance windows. Too little oxygen prevents reduction of the ore, while too much oxygen oxidizes the metal and reduces quality. Ancient smiths had no thermometers, no pressure gauges, no chemical laboratories, and no written formulas, yet they consistently produced usable iron. This suggests the existence of an accumulated body of technical knowledge transmitted across generations. Some researchers compare this lost expertise to Roman concrete technology. The Romans produced marine concrete so durable that certain harbour structures have survived nearly 2,000 years of wave action. And modern scientists only recently began understanding the chemical processes responsible for its longevity. Brahmagiri presents a similar puzzle. The artifacts survive, but the knowledge does not. How did smiths determine the ideal charcoal-to-ore ratio? How did they recognize optimal furnace temperatures? How did they identify the best ore deposits without geological surveys? How did they train apprentices to reproduce successful results? Archaeologists can reconstruct parts of the process, but many operational details remain unknown. The formulas that once existed inside the minds of ancient metallurgists vanished long ago. What remains are the products of that knowledge. Technology does not emerge in isolation. The sophistication visible at Brahmagiri raises questions about how information moved across ancient India. Iron-working knowledge likely spread through networks of craftsmen, traders, and specialists operating over large distances. Yet no technical textbooks survive, and no instructional documents explain the transfer of metallurgical expertise. The situation resembles other ancient technological mysteries. The builders of the Egyptian pyramids moved millions of stone blocks, but left few detailed construction records. The creators of the Antikythera mechanism built an astronomical computer nearly 2,000 years ahead of its time, Yet no instruction manual has ever been discovered. The inhabitants of Brahmagiri mastered iron production, but the educational system that supported that achievement remains invisible. The scale of Brahmagiri's megalithic landscape implies organized labor, constructing stone circles, quarrying slabs, building chambers, producing tools and conducting burial ceremonies required coordination among large groups of people. This suggests leadership structures capable of planning complex projects. Who directed these activities? Were there specialist engineers, professional stoneworkers, master metallurgists, or religious authorities controlling labor resources? The archaeological evidence provides hints but no definitive answers. The physical remains demonstrate organization, but the social mechanisms remain largely hidden. What do you think? Did the people of Brahmagiri possess technological knowledge far more advanced than historians currently recognize? Or are we simply underestimating the ingenuity of ancient engineering? Share your thoughts in the comments below. Pirana sits in Haryana, northwestern India, near the dry channels of the ancient Gaga River. What archaeologists uncovered here may force us to rethink when one of humanity's most advanced ancient civilizations truly began. Some radiocarbon dates suggest that people may have been living at Pirana as early as 7,500 BCE, thousands of years before the mature cities of the Indus Valley civilization appeared. If those dates are correct, one of history's greatest technological traditions may have roots far deeper than anyone imagined. The site was excavated by the Archaeological Survey of India beginning in the early 2000s. Beneath layers of Harappan occupation, researchers discovered evidence of much older settlements, including early pottery, domestic structures, storage facilities, and traces of long-term habitation. What seemed at first to be a typical Harappan settlement gradually revealed a much larger mystery, a technological development sequence spanning several millennia. For decades, historians believe that the Indus Valley civilization emerged gradually between roughly 3,300 BCE and 2600 BCE before reaching its mature urban phase. Pirana complicated that narrative. Radiocarbon analyses from some of the deepest occupation layers suggested dates reaching back to approximately 7,500 BCE. Not all researchers agree with these interpretations, and the chronology remains debated. Yet even conservative estimates place some occupation levels significantly earlier than many traditional Harappan timelines. The implications are enormous. The Great Pyramid of Giza would not be built until around 2560 BCE. Stonehenge's main phases would not begin until around 3000 BCE. The earliest Mesopotamian cities would emerge thousands of years later. If Pirana's earliest dates are accurate, communities in this region were already experimenting with settlement technologies while much of the world was still dominated by mobile hunter-gatherer societies. The mystery is not simply the age of the site. The mystery is how technological knowledge appears to accumulate so steadily across such a vast span of time. Most ancient settlements show interruptions, collapses, abandonment phases, or abrupt cultural transitions. Pirana instead appears to preserve something far rarer: continuity. Today, the surrounding landscape is semi-arid, yet ancient populations would have required dependable access to water for agriculture, livestock, pottery production, and daily survival. Geological studies suggest that the region once benefited from river systems far more active than those visible today. Many researchers associate Pirana with the broader Gaga-Hakra Paleochannel network, often linked to debates surrounding the legendary Saraswati River. The challenge is understanding how ancient inhabitants adapted to environmental change. Climate reconstructions indicate that monsoon intensity fluctuated significantly during the Holocene period. Water availability likely changed repeatedly over centuries, yet occupation continued. This suggests the inhabitants possessed a sophisticated practical understanding of hydrology. How did they predict seasonal changes? How did they manage water storage? How did they maintain agricultural productivity despite long-term environmental instability? Unlike modern engineers, they had no satellites, weather stations, or hydrological models. Yet their community survived for generations. The technical knowledge that made this possible has almost entirely disappeared. Perhaps the most astonishing puzzle at Birana is not architecture, agriculture, or chronology. It is pottery. To many people, ancient pottery appears simple. In reality, ceramic production is one of the most technically demanding crafts ever developed. Every ceramic vessel represents a complex interaction between mineralogy, chemistry, heat transfer, moisture control, and material engineering. At Birana, archaeologists discovered evidence showing a remarkable progression from early handmade ceramics to increasingly refined pottery traditions that would eventually become characteristic of Harappan culture. What makes this sequence extraordinary is its continuity. Across centuries and possibly millennia, pottery quality generally improved rather than deteriorated. This raises a profound technological question. How was knowledge preserved so effectively for so long? Modern ceramic engineers understand that successful pottery production depends on precise control of numerous variables. Clay composition must be carefully selected, impurities must be managed, temper materials must be added in correct proportions, drying must occur at controlled rates, firing temperatures must reach specific ranges, and cooling must be gradual enough to prevent cracking. Even today, industrial ceramic production relies heavily on instruments and measurements. Ancient potters possessed none of these tools, yet microscopic analysis of Harappan ceramics reveals remarkable consistency. Many vessels display uniform wall thickness, controlled firing conditions, and highly predictable structural properties. Experimental archaeologists attempting to recreate ancient ceramic technologies have repeatedly discovered that apparently simple pottery often requires extensive practical expertise. Some firing temperatures may have exceeded 800 to 1000 degrees Celsius. Maintaining such temperatures without thermometers demands extraordinary observational skill. Potters must judge heat by flame color, smoke behavior, kiln acoustics, and experience accumulated over many years. But Birana introduces an even deeper mystery. The pottery tradition appears to evolve gradually rather than emerging suddenly. This suggests that technical knowledge was being transmitted successfully across countless generations. Imagine preserving a highly specialized manufacturing process continuously for 2,000, 3,000, or even 4,000 years without textbooks, technical manuals, universities, or written engineering standards. Such continuity would be difficult even in many modern societies. How were apprentices trained? How was quality control maintained? How were innovations preserved? Archaeology provides the products, but the manufacturing system itself remains largely invisible. In many ways, the ceramic sequence at Birana resembles a technological archive. Each layer of soil preserves another chapter in a forgotten engineering tradition. The vessels survive, the engineers do not. One of the defining characteristics of the mature Indus civilization was standardization. Across enormous distances stretching more than 1 million square kilometers, settlements often used similar brick ratios, comparable weights, and surprisingly consistent production methods. Birana may preserve some of the earlier stages of that process. The question is simple but difficult. How does a civilization achieve technical standardization without obvious centralized control? Modern manufacturing depends on regulations, documentation, training systems, inspections, and communication networks. Ancient societies possessed none of these advantages, yet Harappan technologies frequently display consistency that rivals far later civilizations. The roots of that achievement may extend back into settlements such as Birana. Unfortunately, the mechanism remains unknown. Did the people of Birana simply accumulate practical experience over countless generations? Or are we looking at the surviving traces of a technological tradition far older and more sophisticated than history has yet recognized? What do you think? Let us know your thoughts in the comments below.